gonna get started really quickly. So hello, welcome. We're doing our critical design review for Crescendo, which is the FAR 51025 competition rocket. And I'll hand it over to Josh, our project manager.
All right, so yeah, I want to thank you all for coming. Like you said, this is the CDR for a 10K competition rocket. I'm Josh, I'm the project manager. Yeah. Oh, how do I switch it? Okay. Okay. So yeah, so kind of the way things are going to go today is I'm going to go over the scope of the project, just an update on that. It's going to be a little similar to how PDR was done, but just with a little more detail for that. I'll give another overview of the overall rocket. We'll go into the ConOps and the ground operations for pre-flight, and then we'll get into the subsystem designs. So yeah, so again, the goal of this rocket is to compete in FAR's 10,000-foot rocket competition. So the goal is to design, build, and fly a rocket with these following parameters that were taken directly from FAR's competition document, which for PDR hadn't been officially released, but we kind of knew what it was going to have. But now that it's officially released, these are the exact kind of targets that we're trying to hit. So the first one being the actual target apogee, so trying to hit as close to 10,000 feet as possible for a maximum of 10,000 points. For every like foot below or above, we'll lose a point. So yeah, you want to get as close as possible. One of the optional extra points we're doing is recording and transmitting onboard video throughout the entire flight. That'll give us another 500 points. And then the other optional one is experimental data from a CubeSat that'll be talked about later on in the presentation. And then the last thing is not a optional objective. It's we need to transmit and measure flight data throughout, so GPS, telemetry, that sort of thing. And yeah, that's a competition requirement. And so from these, we defined our level 1 requirements, which I went over in PDR, but I'm going to go over again because they've changed just a little bit. So yeah, and then so kind of the goal of this presentation is to go over the takeaways from PDR, the next steps, and how we've kind of approached those. Go into more detailed design and performance analysis that we've done, testing, manufacturing, and assembly plans that we've integrated now, and then budget estimates. So yeah, so the level 1 requirements, the big change was to the 1-1 requirement, which before had a slightly larger margin, but now that aerodynamics has kind of reined in their performance simulations, they're a little more confident about the range that we can hit. So the goal now is 10,000 feet plus or minus 650 feet. The second one, again, drawn from the just kind of not only competition objectives, because if we don't land the rocket safely, we don't get any points at all, but also just kind of a safety thing. Yeah.
So I have a question for your verification measure for requirement 1-1. You have testing on there. Are you planning on doing a test flight of the rocket before FAR?
I guess that's a fair. No, I don't think so. I don't think that's a plan. I guess a better. It's more testing of the components than it is testing, because like for, yeah, more testing of specific parts rather than testing of the whole. Yeah, Ryan.
That should be 10,650 plus or minus 650.
10. Say that again.
We wanted it above 10. We wanted 10,000 to be the minimum.
Minimum. Okay. All right. So it should be just plus.
Plus or minus 650 still, but it's 10,650. So that's.
Oh, okay.
It'll be on our slide.
That's right. And yeah, they'll go over a little bit more about how that metric was picked. Yeah. So the third one, providing live video coverage on the grounds throughout the flight. Again, that's a competition kind of requirement that we've now set for ourselves. Tracking position and telemetry data, again, another competition requirement, and then supporting the BrainSat payload, which we've all defined as being kind of critical design considerations. And so those kind of drove the rest of our design. So yeah, and so kind of an overview. It's a little bit of kind of hard to look at, but I'll go in. We have some CAD that kind of makes it a little bit easier. But just for overall kind of statistics, the weight is going to be about 30 kilograms, plus or minus a little bit. Length is 230 centimeters, and then it'll have a stability caliber of 1.7. And so kind of breaking into the components, profile-wise, we have our nose cone, we have 3 body tubes, we have a bow tail, and then we have 4 fins. And then breaking that up to the internal parts, we're going to have a recovery vessel in the top body tube section. It'll have a aluminum coupler on both ends. We'll have the avionics and payload stack in the middle body tube. And then between the middle and lower body tubes, we have a aluminum coupler that kind of will integrate the payload stack and then also kind of bump up against the motor mount that's in the bottom tube. And so, yeah, more detailed assembly and manufacturing for each of those will be gotten into in a little bit. Yeah, that's the plan. And then just another view to see just everything kind of all together. So yeah, so getting into the ConOps, we've broken it up into 7 phases. We have the launch, we have our burn phase, coast phase, apogee, drogue deployment, main deployment, and then landing. And then as you can see throughout the whole thing, up until the landing phase, we have telemetry and video streaming occurring. And then when the rocket lands, we'll cut off video feed and just have telemetry so we can get positioning data. And so just to go into a little bit more detail of what systems are operating at each phase, during launch, our entry condition for launch is it's placed on the pad, the arming rods for the avionics system are removed, and then we have our igniter attached. So it's once we're kind of walking away from the rocket and we're sure it's all set up. And so once it's activated, the next move is to wait for avionics to connect to it to make sure that there's connection for video and telemetry. Also at that time, experimental data will start being collected and just continue throughout flight. And yeah, once we're able to make a secure connection, we're all set to go. We'll begin video transmission and then set up the ignition system. And so once the rocket leaves, that'll be the end of launch or leaves the pad. And so the next phase is burn. And so it's once the rocket leaves the pad, and this occurs while the motor is, operating. And so during this time, navigation systems are detecting and sending information. Telemetry is sending data. CubeSat is recording data, but it won't be sending it. And then, yeah, once the motor finishes burning, we enter into the coast and apogee phase. The rocket is now descending on its way to its maximum altitude. And so again, navigation system is still operating as it was. All transmission is continuing. And then this phase will end once the avionics system starts detecting a negative velocity. So once we're on our way down. And with that negative detection, we start the drogue parachute deployment, which will basically yeah, question?
Sorry, how are you detecting velocity?
I think it's a accelerometer, would it be?
Altimeter.
Is it an altimeter?
It is derived from a barometric altimeter.
Okay.
How are you filtering that data? Or are you just using like
There's a pre-made battle logger CF altimeter that has pinouts for pyro that activate on negative velocity at apogee.
And it's any negative velocity, right? Like as soon as you go below 0 at all, or is it like a predetermined negative?
The online stats for it say it has apogee detection. I'm assuming that just means negative velocity. We'll have to do testing. We have it in our testing plan.
Right, but it's constant. It's you guys aren't designing it.
Yeah.
Yeah. So then once we're on the way down, that will deploy Peregrine system, which will fill our recovery vessel, shearing shear pins, and then pushing the nose cone off. And then with that nose cone being pulled off, it pulls out the drogue chute, which deploys, and then we kind of continue descending at a reduced speed. And
Peregrine, is this like a brand name?
Yeah.
That's your decoupler?
Yeah, it's if you see, I don't know, like these things right here, they're little basically CO2 canisters that will be ignited and kind of fill up that vessel.
You guys done ground testing on those?
Not yet, but there's planning for that. We're going to test that system before we do anything with it.
Strongly recommend, because I remember Berkeley failing at bar because their decoupler failed and it was a CO2 system.
So yeah, we're definitely. It's good to know. Yeah, we definitely plan to test that before. For black powder and for separation. I think it was just no one right now is familiar with black powder and just kind of how to do that. And so this was just a simpler system in our heads.
Sounds like a good reason to get familiar with black powder.
It is a little bit less complicated than the black powder two-wire storage.
That's fair. Yeah, again, it's just kind of our first design of a kind of recovery system. So once we get testing, then we'll kind of have a better idea of how, how useful this method is, or if we need to reconsider anything.
One thing that we'll just add before you guys go on is this just a cutoff stage. Once we go into once we kind of finish this mission overview, we'll go into the specific subsystems, and then we'll have the actual leads for those subsystems who better be able to answer these questions as well. So I would just strongly suggest to hold the questions for the, until we get to the subsystems.
Why do you need the drone?
I think it's a FAR requirement is that you need dual deployment. Yeah, so once we reach 10,000 or 1,000 feet, the altimeter detects that and then deploys the main chute, which is on a tender descender, which will be pulled out kind of by the drogue already. And so that'll deploy, and then we reduce speed at an even slower rate until we hit the ground and we detect a 0 velocity. And so at that, we've now entered the landing phase, which basically means we've touched down. Video transmission will cease to kind of conserve battery. Telemetry will continue so that we can kind of try to locate it easier. And then, yeah, we commit to like whatever recovery method or recovery procedures of getting out there and recovering it. And so, yeah, that's kind of an overview. And then I'm not going to go into too much detail on this, but this is basically leading up to operate. Like this is kind of just an overview of pre-flight and then just kind of overview of everything. And so we just have pre-flight assembly, and so a lot of our design is in being considered with how we're going to assemble it on launch day and how we're going to transport it to the launch site. And so that'll be kind of more apparent once we go into assembly. And then mounting, activating, and then yeah, the rest of the stuff that I kind of just went over. But yeah. So yeah, so starting things off, we'll have our aerodynamics lead, Will, kind of talk us through that.
Hey everyone, my name's Will. I have some notes on what I'm going to go over today. So if you guys want to pass these around, if it make it do that, that'd be great also. Before I get started, you know, I really wanted to thank my team for being there. I appreciate all of the hard work and everything. So yeah, we can go on. So objective, make a dynamic piece. Our main objectives were designing the main profiles, considering stability, aerodynamic performance, and manufacturability during that process. We also performed analysis in order of these profile designs in order to gauge the flight performance through simulation and research as well. The main updates from PDR, more detailed flight trajectory estimates with further accuracy, more accurate simulation windows, clear design choices and drawings, and full manufacturing integration plan of profiles. So during CDR, we'll first go over the flight trajectory or the flight performance and simulations. That includes simulation through MATLAB, OpenRocket, RAS Aero, as well as CFD analysis as well. And then we'll go over profile manufacturing, so the manufacturing process of the profiles that we design through the process. Next slide, please. So the first section we'll go over is flight performance and simulation, also headed by Ryan here, who helped out a lot with this process. Next slide. So our target apogee, 10,650 feet. Also with the apogee range of 650 feet. So our apogee range includes apogees from 10,000 feet to 11,300 feet. The target apogee represents like the absolute desired maximum altitude of the rocket during launch, whereas the apogee range that having an apogee within that range, we would consider a success during the launch. If we were to land outside that range, so if the apogee were to be under 10,000 feet or over 11,300 feet, we would consider that, you know, not a success, and we would reevaluate our simulation models and consider it like our simulation models to not considered something during the launch and reevaluate. The maximum velocity was set at Mach 0.9 or 309 meters per second. That was to avoid transonic flow during the flight. And our CD versus Mach graphs also depicted that around 0.9 is where we would experience that and higher drag because of that transonic flow. And then the target stability was set for 1.5 to 2.5 cal. just to give us consistency during our flights. Yeah, to give us a consistent flight trajectory. Does anyone have any further questions on that?
You guys, what's the, it's not constant, right? Like, it was iterative.
Yeah, so we'll talk about it more in some later slides, but yeah. We use CD data from Open Rocket as well as CFT, right? So
Yeah, and how are you targeting an apogee? Do you guys have active like drag control or no?
no, we do not.
Right. So is 10,650 like an output from the model, or do you guys actually target 10,650 and change things in the design to like let's say you're gonna overshoot, change things in the design to allow you to go down?
Yeah, so what we're working on right now is that we initially overshot 10,650 by a lot, and then like we're gonna go through a process where we'll add mass later to in order to bring the apogee down to that range. But we'll go over it more in detail in later slides. Yeah, and then also a few considerations for the apogee range. I guess I forgot to mention. Competition placement, we want to place well in the competition, which is to get 10,000 feet. We felt that being, even with the window at the maximum range of 1,300, even if we were to hit that, last year, the second place team got, I think, 1,250 feet outside 10,000 feet. So we would still place well nevertheless if we hit the top of our window. And then also manufacturing and launch site conditions, so wind as well as manufacturing. Those are factors that could bring down the apogee of the launch vehicle and flight trajectory, which is why we, as a whole, plan to overshoot the goal of 10,000 feet, as well as future competitions. If we decided in the future as a club to pursue the 10K FAR competition again, we decided to overshoot as well, because then we could easily transfer the design of this rocket so that if we wanted to add, for example, like a drone or some of the other competition rules that are in the document that we do not currently have. So it would be easy to iterate over future competitions. Next slide, please. So the motor that we plan to use is the Aerotech M1939W. We chose this motor because of the high thrust combined with the low burn time. The low burn time gives us consistent results within the flight trajectory. The high thrust gets us to over 10,000 feet with the current with the mass and the design that we currently have. We also chose this motor because of some of the ranges before it also kept us below the maximum velocity as well. So you can read the specifications there. Thrust curve looks pretty cool.
The thrust curve is just from manufacturer, right?
Yes, yes, and was produced on that. Yeah.
That's like, what is the sampling frequency of it? It's like half or like 2 hertz or so. Like what granularity do you have points in that thrust curve?
Right. So this is actually taken from MATLAB, and it's like a thrust curve that's I think it's like every half second, but also it's not like perfectly from the manufacturer. Yeah, I think it iterates over like every half second from like the manufacturer's thrust curve, but it resembles it pretty closely, and it was used during our simulations.
Gotcha. So how did you generate the thrust curve then? Then if it's not like directly from the manufacturer?
Oh, I can answer that. It actually is from the manufacturer on their, there's like the motor file has all the points that, and then there's 13 points. That's why it's every half second. We plotted it on MATLAB.
It says that the motor is going to get shipped directly to the launch site. Maybe this is a question more for manufacturing, but if we're not going to have the motor until day of launch, do we have any other way of verifying that it's going to be able to fit into our mounting tube?
I assume that there's specifications for the motor dimensions. We could pretty easily recreate, something the same.
And I'm also pretty sure that we have 98 millimeter. It's a 98 millimeter casing, right? Yeah. We have other 98 millimeter casings, which will be the same nominal dimensions as the motor that we're using, if not the same length, at least the same diameter, which is a more important measurement. So we'll be able to approximate it.
Yeah, you guys are using the aluminum cases up in the hangar, right?
Do we have one that's this? I don't know if we have one that's the right length.
We can purchase the casing for the thing. It would just be kind of the grain, because we have to buy that separately anyway.
Right.
So it would just be shipping the grain directly to FAR, and then we could buy the casing without it being an issue.
Gotcha. Yeah, I would just double check with what we have in the hangar. Because again, I want to say that we have some 98s, and then if your grain is shorter, I'm pretty sure you can. It's like that.
Yeah, I know if the grain's shorter, we definitely had spacing, but I don't know if there's one that's long enough.
Gotcha. Okay.
It is what that makes sense.
What's better sending it straight?
Does anybody have an L2 here? That's probably what. Or an L1, I guess. Like you do an L1, you get L2 grains, but
This one's an L3.
even better.
Yeah, that's the other.
Nobody knows that little piece.
Yes.
Were there any motors in consideration that were lower, like L2s in consideration?
Yeah, I believe we had one lower one. We went over it during PDR, but however, it would not reach our acquisition goal and gave us inconsistent results during flight trajectories.
Okay.
I believe it's also Aerotech, but I don't recall the number right now, but we did go over it in PDR. If you wanted to check that. Next slide, please. So now I'd like to introduce Jack, who helped out a lot with the CFD analysis. Yeah, go ahead.
What's up, guys? I'm Jack. I'm going to be talking a little bit about the implementation of the CFD for Crescendo. So the general overview of what we did is we're basically implementing the Navier-Stokes equations in computational fluid dynamics, and we're solving for the flow around the vehicle. The goal in this is to just get various aerodynamic forces, and in our case, we want drag and pressure. Those are the two forces of most interest. Some of the goals that we had going into this, again, predicting drag coefficient at different Mach numbers comparing to our other results, OpenRocket, RSAero, MATLAB, etc. And then another goal we had was to use this drag data to better approximate our trajectory, flight performance, and behavior of the vehicle. And then another goal was to use the generated pressure gradients at different stages of flight, as well as boundary layer profiles in order to assess the stresses on the vehicle, pressures, velocities, and then use that to better aid in manufacturing and structures down the road. So this is an important aspect of the CFD simulation. This is the flow domain. So you can actually see the rocket. It's like it's super small. It's a little speck. So we had to make sure the flow domain was sufficiently large. Some of the boundary conditions that I applied to this flow domain, you can see on the left side, that's the inlet. This is a velocity free stream inlet. And then this is the outlet here. It's a pressure outlet. And what's cool is we did this simulation in Star CCM. And Star CCM has a built-in standard atmospheric model. So for the free stream on the left, all we did was specify a Mach number and an altitude. And then we ran the CFD at each Mach number we were testing and got all the parameters we wanted, which is cool. Also important, the top and the bottom were walls to simulate, like a big wind tunnel. And the flow domain we ensured was sufficiently large so that there was no interference from the walls that would affect the drag of the vehicle. Some of the main assumptions as well. As you can tell, it's a 2D model. I did some research into this, and I would consider this a pretty low fidelity simulation. 2D was sufficient in our case. Our main goal is to validate some of our other results with the CFD. So we decided to go for 2D. Assume the flow is compressible throughout all the Mach numbers. We're going greater than 0.3. So we wanted to say compressible, ideal gas assumption as well. Flow is steady, turbulent. And then I also enforced the condition that all the flow coming from the inlet to the outlet was strictly on the positive X. The coordinate system is like, you can't really see it, but this positive X direction, nothing going up, down, or into or out of the page. Again, standard atmospheric model, K epsilon turbulence model was the selected model. And yeah, that's pretty much it with the flow domain. And then a little bit.
Sorry, you guys didn't do any shear forces on it?
No, we have not.
Okay, what happens if you like a strong gust of wind?
So for this simulation specific, we're just assuming zero angle of attack. The turbulence model, I looked into it a little bit, and it does simulate some shearing at altitude. I could look more into that if you'd love. Yeah, I could do that. That's a good.
Yeah, I don't think it's gonna be like any this, but like.
Yeah, but this,
I
I should have mentioned as well, this is assuming no angle of attack, just like straight up. So,
that's fine.
okay. So a little bit more about the meshing process. What I did is I applied a 2D automated mesh. A little bit what this is you're solving, continuity, momentum equations, all the Navier-Stokes equations, each one of these little control volumes. So what you want is you want more of a denser mesh near your areas of interest. So you can see like right by the rocket, it's a lot more dense, and then farther away it's less dense. So this is the 2D automated mesh, and then I applied some custom controls to it. I did a volumetric control right by the nose cone. You can see a little like circle, make it a little bit more fine on the nose cone. And then I also applied a surface control after the vehicle downstream. So you can see it's like coming out to the right. And then I also increased the number of prism layers, which prism layers are these along the surface. There's actually almost 50 of them, which you can't see that, very small, and that was to better capture the boundary layer that would develop along the surface, which was very important for our drag predictions. And then this is, yeah,
it's super uncritical for this, but like as you move, like assuming you want to do aero stuff in industry,
yeah,
it's good to just post up the number of nodes and elements.
What was that?
Posting like number of nodes and elements.
Okay. So like just like,
all detail, but
so you'd say just like the number of nodes for each different.
yeah, it's just like showing like this model has like 100,000 elements. I don't know, whatever. I think it's helped you a little better understand.
Thank you. I appreciate that. Thank you. So this is the drag coefficient I came up with. The method that I used to produce this curve. We took our maximum predicted Mach number from MATLAB and some other methods, 0.9 as Will previously mentioned. And then I picked a very representative 20 points between the maximum Mach number and then launch of 0 Mach. And I found the corresponding altitudes as predicted by our MATLAB simulations, which we'll talk about later in the presentation. Inputted those 2 parameters into the CFD for each case, ran it, and then once the coefficient of drag properly converged, usually about like 1,000 iterations, just took note of the CD and then plotted the curve throughout all of those test cases, those 20 cases, and then the reference area I used for the drag coefficient was just the core length of the rocket, which was 2.2 meters. And then these are our results. You can see on the top left, we have a pressure profile, top right velocity profile, and at the bottom is an illustration of the weight. These were all produced at maximum dynamic pressure, which was also found through MATLAB. And, we hope to use these illustrations and some of our data to, again, aid in future manufacturing structures. And you can just see the boundary layer profiles like this right here. So that might help with materials, etc. So we hope to use this going forward. And yes.
Do you have any idea what causes the asymmetry in the wake on the bottom picture?
Yeah, so it's I believe what my understanding is it's the turbulence model mostly, and then it's also the transition from laminar to turbulent. You get those, vortices shedding from the tips of the fins. That's my understanding of it. And we wanted to again make the mesh a little bit more fine downstream of the vehicle because this wake, you have more shear when you have turbulence. So having that wake simulated with more fidelity definitely helps predict the drag a bit better.
What was your dynamic pressure?
I don't have it noted here. Do you have it in the? We can get back to you on that.
And then just making sure that your dynamic pressure is being accounted for by whoever's running the structures on it. I hope you guys are running some sort of structures team that is taking this as an input. Just to make sure.
We can talk and figure that out. All right, thank you.
Yeah.
And then, yeah,
Are you guys accounting for any changes in temperature, like your own time aero, not aerothermal?
with STAR, again, there's a built-in standard atmosphere, so each time I ran the CFD, it does account for, we have those altitudes, and each altitude it runs the standard atmospheric model. So you get density, pressure, temperature, just assuming, linear gradient.
Yeah, and then are you checking like stagnation temperature at your nose?
I haven't gotten to that.
I don't think it will be a huge problem, but something
I
you can
can
consider.
I can look into that.
Like once you start going like supersonic, then it starts to be a problem. So
Yeah.
you guys, but
Okay, yeah, we're going up to point nine.
Yeah.
So, okay, thank you. And then, yeah, it was a great learning experience. I mean, I learned it in 2 weeks, so thank you.
Okay, so for our flight trajectory simulation, we conducted it on MATLAB. We estimated the full trajectory, velocity, acceleration using ordinary differential equations based on the different drag data that we received. So the drag data that we used for this open rocket RAS Aero, as well as Star CCM. Some of the assumptions: rocket treated as point particle, gravity drag, thrust forces acting upon it. Wind, we did not consider wind in our model, as well as rotational motion as well. And the 3 phases that we use: the burn phase of the motor, when the motor produces thrust, the coast phase until apogee, as well as the recovery phase. We added it into the model as well. And here's a graph of our CD versus Mach. This one is from our CFD data, RAS Aero data, and open rocket data. Does anyone have any questions about that? Cool. So to briefly explain all the MATLAB code, if you guys wanted to pull up all the code, posted in Teams, as well as the notes, and the aerodynamics team includes all of the code. But to briefly go over it, the flight trajectory simulation on MATLAB, it uses the standard atmosphere model in order to get pressure and density and temperature at the given altitudes. Forces and moments. So as part of aerodynamics, we have the drag data from MATLAB, Open Rocket, or from Open Rocket RAS Aero, and the Star CCM CFD results all plugged into that as well. Propulsion that happens during the burn phase with the thrusts, and the thrust curve that you guys saw earlier, that's plugged into the model. Gravity always acting down as well. Mass, so we get we assume a linear burn of the motor as well, so the mass will decrease during the burn phase as well. And then our ordinary differential equations that solve for the difference in mass, velocity, and height of the rocket during its flight trajectory. Does anyone have any questions? Yes.
So which CE estimate did you use for this?
We use all of them. Yeah, you'll see shortly.
Like, did you average them, or did you do like one for each? Or
Yeah,
One for each. That's the next slide.
Yeah.
Also, Will, I don't think we implemented the temperature into, did we?
Into
our actual trajectory.
Yeah, into the calculations, it was not considered, but it was stored as a variable. Yeah.
Okay, and here are the results from the 3 different tests using Open Rocket, RAS, and Star CCM drag data. You can read the numbers for yourself, but there's a big difference between all of them. Open Rocket is the lowest with 11,500, and RAS is the biggest with 12,300 feet. You can see the comparison over there, and the reasoning are assumed reasons behind why it's different we'll go over in a bit, but yeah, here's the data from MATLAB.
One important note to point out is that this is the flight trajectory based on our current design without mass added, which we plan to do before, after manufacturing, before launch.
Yeah, that's why all the altitudes are so high. There's a slide coming up later where we drop it down a bit to match our requirements better.
Yeah.
Are you taking into account how the stability of the rocket's going to change once you add that extra mass?
Yeah, so I guess we'll speak more to it later, but the mass is going to be added near the center of gravity in the bottom coupler, so it won't affect stability too much.
Okay, and this one is Open Rocket's trajectory model using the extended Barrowman calculation method. Don't know what that means exactly, but I trust Open Rocket. We made some changes from PDR. We added the surface finish was brought up during PDR, and we brought it down to a surface finish that we feel is we can accomplish. It'll be mentioned later in the manufacturing section of our aerodynamics presentation. And we added the mass from couplers and other masses that we didn't account for during PDR. We were using just like strict limits of how much we were going to give to each section, and it's less than that. So we with the added coupler and the drop in the subsystem masses, it kind of evened out, but it's more accurate now. Open Rocket's model, well, it's the same. It's pretty close to the MATLAB model using Open Rocket's drag data, but it's a little bit lower, I believe. Max velocity is within our range that we would say is safe. Yeah, and you can read the rest of the data. Any questions in that? Yeah.
I know that you said that like you don't know what like the extended Durbin's method is, but I think you should definitely take into account because they make different assumptions each one. So you should know what the assumptions are when you're comparing each trajectory.
Got it. Good. No, thank you. Okay. RAS uses Rogers modified Barrowman method. Again, I don't know what that is, but I will look into it more. So for PDR, we only use the CD data from RAS that we could use that for our MATLAB, but this time RAS has its own built-in flight trajectory. So for this, we use all the same data as Open Rocket. Like we put in the CG and CP that Open Rocket gave us. And yeah, their altitude is a lot higher than we thought it would be. And the velocity is a little over what we would say is safe. But again, we're going to add mass in a few slides to see how much we can bring it down and still keep all our simulations within the window that we set for ourselves.
And some reason we believe that the RAS model was giving us
got that in a higher slide. Okay, simulation results. Here's just some graphs of all of them together. All of the flight trajectories from the 3 MATLABs we did, the Open Rocket and the RAS. They're color coded down here. It's kind of hard to read though because it's far away. We also have the velocities, and I believe the RAS MATLAB and the RAS just by itself have velocities that go over what we set. Yeah, so that's not good, but it'll be addressed in a bit. Any questions on this? Okay, and here's why we think there's some variance. Definitely the drag coefficient, if you saw it earlier, they were going in opposite directions. One of them was going up as Mach increased and the other was going down. That's definitely one of the reasons why Open Rocket and RAS are coming out with different numbers. The angle of attack for Open Rocket fluctuates a lot, and the RAS one stays pretty flat. And that's the same thing with the MATLAB ones we ran, also had flat angles of attack. That's why Open Rockets is probably the lowest because the other ones were assuming perfect angle of attack. Any other considerations?
So for our mass estimation, for adding the mass later in the process of manufacturing our rocket. So mass will be added to the rocket post-manufacturing in order to bring the rocket down within the range, the apogee range, and lower the maximum velocity within our maximum velocity. The simulation here depicts 4 kilograms in added mass to the current design of the rocket. And this 4 kilograms in mass will be added in the form of sand to the bottom coupler. We chose the bottom coupler because it's near the center of gravity and wouldn't affect the stability of the rocket too much overall.
How are you making sure the sand stays in place?
Yeah, so we were planning on putting the sand in like some sort of bag and weighing that as a whole. Yeah. Yeah.
Do you have like an upper limit on the mass for that can physically fit inside of the space?
Yes. 6 kilograms will fit. We just calculated by volume of how much space is in the coupler.
Okay.
Yes. And then we're gonna do this after the manufacturing process because the actual weight of the rocket could end up to be different than the design that we have right now on Open Rocket. So we'll consider that difference within 4-hour mass estimation and then either add or subtract the amount of sand or mass that we'll need to put in the bottom coupler.
And I think you guys are on the right track here, but should be explicit about why you're doing this. Can you explain why you're using sand instead of like something solid, like a slug of steel?
Oh, I think we chose to use sand. I guess it would be easier to like get the perfect amount of mass that way. Yeah.
One part of it, like when you guys go to the bar, they're going to recommend using water. And I think sand kind of feels just like the same requirement. There's a very real possibility that you guys come back ballistic instead of coming back under shoots. And if you slam to the ground and parts go flying everywhere, sand is going to have way less killing potential than the big slug of steel flying in your guys' bunker. So like when you guys are ballasting, like you guys I think made a good choice here, but like for future generations of rocket, don't ballast with something solid, like use either water or sand, so that it kind of just turn into a bunch of little tiny particles inside one big one. If you guys have that listed.
Yeah, it's not gonna happen though. Yeah.
And then the added mass also has a negligible effect on the descent velocity. I had a velocity graph, I just forgot to put it on here. It also lowered the maximum velocity to well below what our limit was. So we're not going to hit transonic as long as this runs as planned.
Do you know what that Mach number is for the updated mass?
0.7 was the lowest, 0.8 was the highest, and our limit was 0.9. Okay, wind analysis. So this, we've got a bunch of different numbers here. No wind through high wind. We looked at the FAR sites on the website, and we looked at like the weather from past years, and yeah.
Is this wind with or without the mass?
Without mass. So we looked at it from past years, and then saw the highest wind was about 13.41 meters per second. Meters per second, and if you're imperial, then miles per hour, it's like 30 miles per hour. No wind. We didn't want to put like actual zero. It's 5 miles per hour. Pretty small. It's the no wind one. For if it was 0 miles per hour and 5 miles per hour, the variance was like identical. It barely changes the apogee for that. And then we put some in between cases just to get a good sense of how our apogee would change with different wind cases. And we ran 20 simulations and averaged these important values just to see how we were looking in those. And we've got a graph over here. So as you can see, the no wind case, we're pretty consistently where the simulations say we're going to land. But then in the high wind, our apogee drops, and then it's a lot wild. It's more of a guessing game as to where it's going to hit. But yeah, all of these yellow ones are still within the range, within like the range that we feel is close enough to the apogee we were trying to hit. Yeah.
So then are there plans then to be able to tailor the mass that we add based off of the wind conditions at time of launch? Are there plans to run simulations?
There were no plans, but there are plans now. Yes, that's something we can easily do.
Okay. Yeah, and the wind also was considered within our apogee range. So like if you see the wind affects it roughly like a few hundred feet, and that's why we had an apogee range of plus minus 650 as well, because yeah, of the wind factor.
Are y'all gonna hold like commit criteria for wind? Like you go out there and like measure wind speed and say, oh wow, we're 13.42 meters per second. Should I stack up, y'all?
No, we do not.
What if wind speed is like hurricane in the Mojave?
Yeah, I would hope the rocket. I would hope nobody would be launching their rockets at a hurricane.
I don't think it's going back once again, but something.
Yeah.
I guess when we went to FAR last year, I do remember when winds picked up, they definitely like stopped launches. So they, at least the facility has a higher limit where they're willing to let people launch.
So there's some line there that you guys are probably.
Yeah.
So our next step, post CDR before the launch, further CFD analysis. So we mentioned some of the further analysis that we can do on the rocket, including temperature, as mentioned before. Wind tunnel testing, we can also gather more results on a real life model using the low speed wind tunnel to simulate the flow across the model, get more drag data, and really see like the accuracy of, or get more drag data for low Mach numbers, since we had some conflicting values there. The RAS arrow data for that was really high, whereas the CFD simulations and the open rocket data for the drag data at low Mach values were really low as well. So doing low speed wind tunnel testing will help us configure that out. Mass certainty and updating, which we went over, measuring the mass of the rocket after manufacturing and correctly getting that and implementing that into our mass calculation. That will be a next step as well as surface finish testing. So the surface finish of the rocket we'll need to gauge after manufacturing in order to update that simulation model in order to get an accurate flight trajectory. Yes, now.
For the wind tunnel testing, I plan to do that on the flight model, and if so, do you have a timeline, just like a preliminary timeline when you expect to be doing that test?
Right. Yeah. So we'll begin like researching the wind tunnel testing after this after CDR. And sorry, what was the first question?
I just mean like, are you gonna like build like your own little model, or you can use the actual like body tube and stuff? And if so, have you like talked with manufacturing at all for when you need that to do that test?
Yeah. So as of now, we're most likely going to use like a 3D printed model that like resembles the profiles. Yeah. That scales down.
You're only going to produce 1.9 in aero. Not bad. Those times can only spin that fast.
Yeah. So it will be sort of the low speed for it, like the very low Mach values that.
Yeah. So that actually a result that will produce output for your eyes.
I believe so, because like if you saw the Mach versus CV curve at the very beginning, it was it was very different, our results between like the RAS and open rocket data. So I think it would be a good process to pursue as well as for experience as well.
Definitely agree on experience, but in terms of apogee, like most of your energy loss will be like at higher Mach numbers, right? Because of higher C and like higher dynamic pressure. So I think I'm kind of with Gar on this somewhat. So this is kind of going into one of my other questions, is like, what open work do you guys have before you give the thumbs up to launch? Like if I told you like we have a rocket that is designed to be your CDR, we're launching tomorrow, would you like say, oh shit, don't launch it? Like what do you like when y'all trying to launch? June. Okay. What are you going to be working on for this rocket between now and June? I guess is the question.
Yeah. So
and how will that change things, right? Because like Aero, other people are consuming your outputs as their inputs, like manufacturing team. So like, what are your due dates? I think is what I'm asking.
Due dates, like I guess after the entire manufacturing process. So whenever that happens, like the mass, that would be one important due date, like is with the mass certainty updating. And that's a good point. Like it wouldn't affect like quote unquote the flight trajectory too much with the wind tunnel testing, since it is at very low speeds. And most of our apogee and launch trajectories happen between the higher Mach values. But I think it probably would be still a valuable experience. But,
that was one other question. What's your guys' velocity off the rail? Like when you go to launch, your stability, like if you have too much mass for your thrust, you won't have enough velocity to actually generate any like corrective force from your fins. Have you guys explicitly checked that you guys are going to be going fast enough off the launch rail to be stable?
Right. We haven't considered that yet, but we can look into it. Yes.
Yeah, it's not like it's super crazy out there. There are plenty of recommendations online in terms of what velocity you should be hitting, and then it's just like people's MA to make sure. But would strongly suggest double check it. You'll probably be fine based on your ask throws. But our guys will probably ask. And I don't know, just have one more question. Von Carmen for the nose cone.
Yeah.
Yes.
And
I think that should have been.
yeah,
Yeah.
it's in the profile section. We went over it pretty extensively during PR. It's in the notes in the profiles before the flight trajectory.
How do you account for distortion in the rail window? What are you assuming for the rail?
For the rail angle, you asked for the launch rails.
Yeah, like how vertical rail is?
Right. So
How do you know that?
Oh, yeah.
in the open rocket model, I believe it was assumed to be 9 degrees. And then, or the RAS arrow, I think was 9 degrees. And then the open rocket model was 11.
Oh, the angle of attack?
Yeah, the angle of attack.
Yeah,
Right.
once it actually came up.
The angle between the rail launch rocket and like you're not gonna point the rail 90-degree upwards. What is the angle that you're actually pointing the rocket?
Yeah, so like the velocity
If you give rocket is leaving the rail not at 90-degree vertical, but at 70-degree vertical. You're producing a much slower.
Right.
What is the angle that you're assuming?
We're assuming perfect 90-degree, and we can test open rocket, I believe, and RAS era also have tests to if you can change the
No
angle.
rail is actually vertical, right?
Correct.
And rails are actually explicitly made to be not vertical, because you kind of want to know which way you're going. It's like a way for you 0.5 degrees downwind, you know you're going into the wind. So you need to look at your hardware and figure out what the angle is, and what that could be, and what dispersion of results is for you if you go 5 degree versus 10 degree versus 3 degree, because that's going to produce like that. I suspect that the magnitude of error that introduces is bigger than all errors that you have put together. So you really need to make sure that like whatever you're simulating is addressing that properly. It is possible that you will simulate this 85-degree angle and launch at 85, but probably not.
Right.
So you need to have an understanding of how that much that affects.
Oh, could I ask you a question? If we have an understanding of how it affects our launch, what should we then do with the hardware to make a correction for that? Like, how would we then, like, what do we do next?
Yeah, so right now you're overshooting that, right? So
Yeah.
you're assuming that you're perfectly overshooting. So you're making uncontrolled potential, right? You should go ahead and figure out what actual angle is. And that's simulating that. Get the understanding of what your allowed is for the error. So assume you were like, right, our error was actually 85 degrees. I have no idea what actual. Okay, if we make it 87 degrees, what does that do to our predicted energy? Or if we make it 83 degrees, that's our option. So plus minus 2, right? Now your plus minus 2 is your requirement. You actually need to make sure that the rail is within the plus minus 2 on launch. So go and measure something in there. You know, make sure that like the pins that control the height, right? And then make sure that part guys are actually going to be okay with you launching at like whatever angle you pick, because they might enforce an angle on you if they decide that the wings are too high, and they want to make sure they're going up. The scare that they have is that the rocket leaves rail is still unstable, and then the wind takes it right into the ground. That's their objective to avoid. Now your rocket will, if it's stable, is going to want to point in the wind. So if you help it a little bit by pointing into the middle, it'll probably be okay. But like the fact that you don't have that angle in the simulation, your numbers makes me very worried about validity.
Thank you. So I have two really quick comments on that. First of all, are you guys launching off of a far rail, or are you guys going to deeper rail?
Off of far rail, I think a
So
10 foot.
20 foot.
Say like
20?
what angles do you have available
Are
to
we
us?
just testing it?
There's not a whole lot of point simulating to like a 2-degree accuracy if they only have increments of like 5 or 10 degrees.
Somebody jump on the car drive up there.
And then the other thing was like kind of like Yara mentioned it briefly, but like this is why stability also rail is super important, because if you're going super slow, then as soon as you come off the rail, if you get a strong gust, it's going to change your angle, and then you like take that for the rest of the flight essentially. So just want to reiterate, like, make sure you double check stability, and then that can also impact your guys' criteria for winds.
So is the plan right now to bring the mass up to some specified amount that will, you think will get you to 10,650 feet?
Yes, yeah.
Okay, so is that, what are you gonna use to estimate to get you to 10,650 feet? Are you just like using kind of the middle between your high and low estimates to get there? Or are you like averaging all of your different trials? Like, cause you have, you know, in some cases, between like the unweighted one, you had like a difference of 800, feet from the top to the bottom. So I was just wondering, how are you going to decide what mass you want on the rocket to hit that goal as close as you can?
Yeah. So by adding mass, we're gonna within those different trajectories that range around a few hundred feet. We're gonna make sure that all of those are covered within like the apogee range of 650 feet plus minus. So that's what that process will look like.
And if you take a look at the different sims on one of the pages, there's a graph with the altitude estimates from each of them using the weighted masses. And it actually like dropped the difference between
which page those on? Because I could only see it for the unweighted and for the wind unweighted.
So the unweighted one, and then you just turn the page, it should be above wind analysis.
Yeah, in the mass estimation section.
It's got like a horizontal line saying where our goal is.
Right, but do you have numbers for those specifically on the graph? You have those apogee numbers?
I do not have them on hand, no.
Then my follow-up question is, if you have a best and worst case scenario, given from your different simulations and different wind amounts, then why would you target 10,650 instead of just targeting 10,000? Because that way your upper and lower range would get you more points rather than being above it. Like I understand that you expect to like go over mass, but unless you guys think those like you see what I'm saying? Like, or if you have an estimation, you have like a probability graph of like how close to that estimation you're going to be. Do you think it's like way offset below what your estimation is, or do you think that it's because if it's perfectly equal to be probable below or minus 10,650, then why not shoot for 10,000 exactly?
Right. Yeah. We chose to set it at 10,650 due to the I spoke to this a little earlier, but we preferred if the rocket were to be over the apogee over 10,000 feet. The apogee were to be over 10,000 feet rather than under, due to the consideration of future launches and consideration of future launches, and because of the slight errors that.
But I'm saying once you add the mass, right? Because for the unweighted rocket, yeah, I agree. We definitely want it to go above 10,000 because we're going to be adding payloads and stuff. We might have payloads in the future that we want to add, but then. Since if you can add mass to bring it closer to 10,000 feet, why not? Is my question.
I believe we will be doing that. The mass number is not a hard 4 kilograms. Since we have up to 6 kilograms, that's a couple pounds of range to add to. And that one was just for these simulations. But I would say it's not as, you were saying probability of going over and under. I would not say it's equal on both, just based on all the considerations that have come up, like the angle of the launch rail, angle of attack, wind, all that stuff. I would say it's more likely that ours would drop because you would need like the perfect storm to hit our apogee at the highest that we set. Right. So if we're assuming the worst, we would still want it to come close to 10,000 because our minimum apogee we would hit with our simulations is at 10,000, and then even if there is like a hurricane or something, then it would drop to below 10,000. But I just don't think it's I think it's more likely that we're gonna end up lower than we assume than higher than we assume. That's why ours is set higher than the actual goal, the FAR goal.
Okay, I would love to see like best case and worst case estimates and like based on launch angle and rail and like get like an actual like this is like worst case what we expect could credibly happen, and then see where that lies if that's close to 10,000 or below it or not.
Right, that's a good idea. Coming back to a question you asked earlier, actually, for the mass with wind, I did take a look at it, and with our 4 kilograms that we were considering adding, the wind the simulations also varied, but they were in the range of like 9,950, I believe, or 9,500, up to like 9,900 was where most of them landed. So that would be still pretty close to the 10,000 that we're realistically trying to hit. But you're right, we would have to take into consideration all the other problems that could happen. So we can definitely come up with a best case and worst case scenario, and that will play into how much weight we're gonna add.
Yeah, so sorry to go back to that point, like I think this is a question for either the PM or president or VP. Like, do you want to target the most points, or do you want to target getting over 10,000 feet for the flex? Like, if you guys are trying to maximize points, I think your name is Kyle. I think Kyle has a really good point. Like, you guys should be targeting 10,000, not 10,650.
Yeah.
But if you guys are trying to go to 10,000 feet as a club, you should be maximizing for about 10,000 with your lower dispersion at 10,000.
I mean, I think to answer that, I think a better way to kind of think about the altitude range is more, it's the range is, the nominal value is 10,000 in our range is plus 1,300 feet rather than 10,650 plus minus. I think that's kind of a better way to look at it. We're looking to hit 10,000 feet, but okay with going over, not as much as going under, at least in our preliminary simulations.
So that's an internal desirement of getting above 10,000 feet. Like, if you are trying to maximize points, you should be targeting 10,000 exactly. Like, for your range, if you assume either a standard distribution or uniform, like no matter how you act it, like you will never maximize points if you're offset compared to being dead even on 10K. But I would probably still go above 10K because I want the flex. But that's just me.
I'll say one other thing. I think part of it, I think the a better way to look at these is this is kind of the simulation target, because there's a lot of assumptions being made in most of these simulations, even the most accurate ones. So I just feel like after manufacturing, we're going to have inconsistencies with our profile. There's going to be bolts going through the body tube. There's going to be things that are going to pull down our performance. There's going to be a lot more things that pull down our performance than there are that are going to make it better.
I don't disagree with that, but if we're saying that that's going to happen, we shouldn't just blindly say, yeah, there's something that's going to fuck us over later. It's like, we should be accounting for that in our dispersions. And then using those dispersions to try and maximize points.
I think it's fine to say that our aerodynamic simulations will overestimate if you can back that up with evidence and say, yeah, we're pretty sure that we're overestimating these for these reasons. That's fine. And as in kind of a subsystem level goal, you could say our open rocket, we'd like open rocket to hit 10,650, but as a system level requirement, it should be whatever you want the system to actually do, which I think in this case is hit 10,000.
Right, that's fair. Yeah.
That was kind of.
That's relative to launch location or absolute
Yes, relative to launch.
Launch location.
We put in the height, the altitude that the launch location is for these simulations we ran.
Yes.
So our standard atmosphere is based on the actual altitude.
Did you look at the dispersion of sea level parametric pressure? Yeah, on a hot day, and Crescendo is going to happen. Parametric pressure is not exactly standard.
We can.
So my more sophisticated then you can find pretty accurate weather data for an airport, right? Different airport source with the miles. So look into that. That might be seriously affecting shopping.
Okay, good to know. Any more questions on, oh, Will.
I know Cal Poly has a blow down supersonic wind tunnel that like can prevent 4 seconds of supersonic flow. Is there, do you know if that can like provide a longer amount of like at 0.9 Mach, so that maybe you could simulate your models?
Yeah,
At least that's something you could look into.
yeah, we definitely look into that, but however, we assume that access to low speed, which it would be accessible.
Yeah, have you seen the supersonic wind tunnel?
Yeah, it's the big tank. And then,
Right, but like, have you seen the actual like cross section of where your model
yeah,
goes?
it's
Like,
very small.
Yeah, we can put one of those in.
Yeah, you can put that in.
yeah. I'm not narrow guy, so I'm like,
Yeah.
I mean,
For the level this point, what are you actually doing to test this?
I'll give you that.
Yeah. If that's all the questions for simulation, we're moving on to manufacturing. Okay, thank you.
Okay, hello, my name is Kendall Wilhite, and I was responsible for putting together the manufacturing plan for the aerodynamic profiles. So a little bit of background about why we kind of started this more in-depth process for the manufacturing plan. Last year with hurdy-gurdy, we had some manufacturing issues, to put it nicely. So we did fiberglass wet layups for the body tubes, and that did end up working fine, but it was a more complicated and messy manufacturing process than I think we would like to undertake this year. As for the nose cone, we did a 3D printed nose cone last year. It did not survive flight, so definitely wanted to make some changes with that this year. And then for the fins, we did pre-made carbon fiber plate. And the only reason we're not going with that for this year is buying plate that's large enough to cut to size for our fins is going to be more expensive than the alternatives I present later. So for this year, with Crescendo, we plan to do carbon fiber and fiberglass pre-preg for the body tubes. I will get into that distinction. We will be using primarily carbon fiber, not in combination. We'll have one body tube alone that's fiberglass. And then for the nose cone, we will be using carbon fiber pre-preg as well as for the boat tail. And then for the fins, we will use an aramid honeycomb core that is sandwich layup with carbon fiber pre-preg over top. Why composites? Composites have a very high strength to weight ratio, as well as they can give us very good surface finish qualities depending on which materials we use. Another point on why we wanted to go with composites, specifically pre-pregs, it simplifies the manufacturing process a lot. So a little bit about pre-pregs. A composite material is a fabric with resin. So for wet layups, you buy the fabric and resin separately and you like paint it on kind of. Pre-preg, it already comes put together. So it does simplify that process a lot. And all we have to do is vacuum bag it and then cure it. So,
What's the curing process for it?
I will get into that a little bit later, but you can either use an autoclave, which is heat and pressure all in one, or you can do vacuum bag and then cure it in an oven. That's what we plan to do. The material we plan to use is designed for vacuum bag processing. So one of the criteria kept in mind when choosing materials was surface finish. So with the open rocket simulations, the targeted apogee ranged about 915 meters, about 3,000 feet, changing the surface finish alone, keeping everything the same, just changing the overall surface finish of the rocket. So this was a big factor to consider when choosing materials. This graph over here, I changed the entire rocket's surface finish, but I also went in and did part by part. So isolating nose cone, boat tail, body tubes, and fins. And determined that the parts that most impacted the overall apogee having a high surface finish were the body tubes and fins. So if anything needs to have a good surface finish, it's those two parts. And our targeted range for surface finish is 125 micrometers plus or minus 25. This range was determined through the open rocket simulations, it doesn't let you necessarily pick your own individual value. They have pre-selected values, and those are stated on the left. And so targeting about 125 should put us within our targeted range. And this was before I think we updated mass and things, so that's why our apogee is a little bit higher than what they previously stated as target.
How do you plan on verifying your surface finish?
We plan to do like test patches, so doing very small layups following our intended procedure, fully curing them and then running them under a surface roughness like dial. Yeah, and measuring just variation in surface finish. So, and then if it doesn't come out to our targeted range, then we will have to, we've looked at it a little bit, but further explore post-manufacturing operations.
Okay, so you're going to qualify the process, and your final article is not going to be direct checked.
We'll check the final article, but just like do preliminary testing to make sure we're not doing the full layup without ensuring that we can at least hit our targeted range.
Gotcha. And then, sorry, going back to the like design team. Did you guys look into like different profiles for the leading edge of your fins?
Different profiles for the leading edge of the fins, I believe.
Yeah, like you assume a square profile.
Oh, we're assuming the ground.
Okay. Just want to make sure manufacturing team is tracking that.
Yeah.
Error doesn't come back with the final article. Who is this matching photo?
Yeah, so I believe in our CAD model, the edges were rounded. And so if I think the plan was to do carbon fiber layups and then cut it to size, just do our own pre-preg layups with the honeycomb aramid core. And then to produce that rounded edge, we can go over with epoxy and sand it to make it nice and round on the edges to match what we have in the CAD design.
If I were to ask you to make a rough surface finish, like produce a rough surface finish, what would you actually do?
To produce a rough surface finish?
Yeah.
If I needed to produce it.
Say we know that the effect of going between unfinished and regular paint is like pretty significant altitude. And you cannot guarantee that you're going to be in the regular paint range all the time. As an example. But you could guarantee that you will always be rough. Because I suspect the trap is you take sandpaper and just sand the whole thing. And you don't even need to measure much after that. So you can very easily make a rough surface finish that you're confident to actually rough. Without even having to do much measurements. What I'm suggesting is maybe you should consider expecting yourself to be rough and actually making it that by sandpaper.
To produce the values on.
Actually,
no, I mean, in terms of your actual surface finish, I think you're more sensitive to workmanship errors than you are if you just try to go fine. Like if you assume plus minus like some percent.
If you cover the whole and you were sending the whole thing down and you make this part of G, that's not actually good.
Couldn't you use peel ply too to get a rough surface finish? You could use something like peel ply.
To at least make it consistent.
Guarantee you a bit more consistent than hand sanding.
Look at the slope of the curve, like the fine range. A small difference makes significant impact on the apogee. And then look at the slope of the curve in a rough range.
Yeah.
Small difference make little difference. So if you make the whole thing rough, yeah, some spots you missed, some spots got like fasteners sticking out, it's super smooth. That's okay. Doesn't matter. Because overall you're pretty rough. So maybe think about that. You're already overshooting altitude according to previous section.
Yes.
So maybe you can just make yourself rough finish.
Yeah. If we
guys just need performance on the table.
If it is a concern, when we do finalize mass and do the wind tunnel testing that we are going to overshoot, surface finish is an area where we can.
I will not count on this. It's pretty significant for the price. You should at this point already be considering that you will try to do that all testing and it might produce productive result, but consider the fact that you might not just pull together in fact. It's like it's a significant undertaking to do. You might just not be able to pull it together in the next operation.
Sure. I guess the reason why we ran these simulations to begin with is if we do have a rough surface finish, we are still within our targeted range. But by maximizing that surface finish, we at least give ourselves like the best platform to push off of. So if other places don't meet their planned requirements for CDR, we at least have an aerodynamic advantage in the surface finish of the rocket.
For what it's worth, I think you're to the right of the anyway, so you're like already starting to approach like a fairly insensitive portion at 125. I think 125 is good target.
Thank you.
Personally,
I appreciate that.
only 60% just
I think that's a good point because there are gonna be fasteners on the outside body.
Yeah.
So if we do all this work to make a super polished finish and then you have a bunch of screws in the end, is the finish gonna make a difference or?
I think it will because it's better if we're gonna have fasteners sticking out anyways and the surface finish is still rough, but like
Makes it even worse,
yeah, exactly.
Anyways.
So it at least kind of balances out the fact that we still are gonna have fasteners sticking out. Kyle?
Well, the simulations we talked about earlier are done with that 125 micrometer
Mhm.
surface finish.
Yeah, the 150 because you can't exactly go.
Yeah, you can't. The values they allow you to select from are few and very far between. So we picked a targeted range somewhere in the middle. Moving on to other criteria that were considered moving into just exploring different types of materials, shear modulus. So we did fin fluttering analysis through MATLAB, and that is almost entirely dependent on the shear modulus of the material you use for the fins. So the MATLAB fin fluttering analysis, we had a safety margin of 10%, and our targeted velocity, this is when it was 0.9, and our safety value was 0.8, and that was with a minimum shear modulus of 3.5 gigapascals. So moving into like material selection when we were looking at technical data sheets, whatever carbon fiber and honeycomb core we used for the fins needed to be at least the 0.5 MSI or 3.5 gigapascals.
What are you defining as your safety margin here?
I think
believe it's the
yeah.
speed that our fin would still be safe. So we use the flutter boundary equation, which would output like when it would start to resonate, I believe.
Yeah.
So that's what the target velocity says. That's why we had our things at 0.9, but we don't want to come even close to that, just like for safety. Just for worst case scenario, if we do hit that, or if we do hit our safety value, we're trying to hit the safety value so that we don't come even close to our target value.
This was using your specific cross section for your fins, right? Like this has to do with the stiffness of your fin.
Yes, it's mostly surface area, thickness, and then the stiffness of the material.
And then another consideration.
Sorry, it should have the like line form area as well, right? Or the length of the fin, because a shorter fin, like out of the fins that you said.
Surface area not including thing.
It should, but like it'll change the moment depending on how that surface area is distributed, right? Like if you have a small ligament leading to a big panel out on the edge, that's going to end up having a huge moment, so it will be able to flutter easily. Whereas if you have it all just like one thin rectangle, it'll be much stiffer.
Right. I don't believe that was accounted for.
As for the upper bounds and the shear modulus, I didn't really want to go above 4.5, solely because making a material too stiff will put us at risk of breaking the fin entirely. So fluttering doesn't matter if the fin's going to completely snap off. So I wanted to keep it between the 4.5 and 3.5 gigapascals. And then our final more mechanical factor when looking at materials was compressive strength. So with the Star CCM fluid dynamic analysis, the highest produced pressure value was the 132.6 kilopascals. And so with this, assuming that pressure is exerting an entirely compressive load onto the rocket, we needed to consider the compressive strength out of whatever material we were using for the rocket. And so that would be, we needed the compressive strength of the material to either meet or exceed the 19 PSI. So that was just a base layer, and there's not, at least from what I could tell, not any downside to going too far over that.
Did you assume 19 PSI across the entire cross-sectional area? Did you like take the pressure distribution and then do an area angle? for total load?
I was just looking at the fluid dynamic analysis and then to the point that had the highest of load, and that was at the nose cone. So it would matter more throughout the nose cone, but I didn't necessarily do it distributed. I just focused.
Yeah, so like my point is like I agree that the highest pressure will be like right at the tip.
Mhm.
The stagnation point is. Did you take that pressure and then just say like we have 19 psi applied across the entire circle, or did you say like if I step over a little bit lower pressure, and so that small area will have lower force acting on it?
I just sort of assumed it for like the whole circular.
19 psi.
Yeah.
I'm good with that.
Okay. And then
Did you only look at like a compressive failure mode, or did you also look at like buckling?
Yeah. I did not. I'm not sure if we considered that later because I did not consider
I'll talk
buckling.
about that a little bit later.
Okay.
What's the diameter of the rope?
I'm sorry.
What's the diameter of the rope?
19 centimeters.
What are your units? Minus 10 points.
190.
So 19.4 inches?
94 centimeters.
What's that in meters?
Wait, that's like 8 or 9.
Yeah, it's,
Yeah, it's 7.5-ish inches.
Oh. That's a lot of force.
So for our final material choices, we were also, I guess, not limited, but the material is donated. So there are only certain materials that they are willing to donate. So that did also limit our list. And so our final material choices were, so for the carbon fiber prepregs from Axiom, they're 5201 products, both the tech variant and the original. So the shear modulus of, and mind you, these two have identical mechanical properties. The only difference between them is this lower carbon fiber is designed to produce a high surface finish for vacuum bag processing. And so that will be used as our first ply and then last ply in our layouts. So the shear modulus of this material was 4.1 gigapascals, which meets our range of 3.5 to 4.5. The compressive strength was 80 ksi, so not anywhere close to the 19 psi. And then the cured ply thickness was 0.22 millimeters.
Oh, sorry. Like that, the 80 ksi versus 19 psi isn't how that works out, right? Like you have 19 psi being applied across your 7.5 inches, and then all of that, like you have a 7.5 inch diameter.
Sure.
The area that load is being carried through is going to be this big.
Sure.
So you're going to get this huge multiplication factor as your compression load goes through your body. So just comparing the 19 psi to the 80 psi is not.
That wasn't something I necessarily looked into explicitly. That is something that I would like to look into more.
Doing that and then also like checking for buckling.
Yeah.
It shouldn't. I think you're short enough that it should be fine, but like applying or like looking at the critical length. And
Yeah.
sure you're within that.
Yeah, that is more doing more of the like stress and strength analysis is something that I would like to do more of after CDR. But for now, like without doing the calculations, I was at least semi-comfortable with the fact that they were so far apart in value, given the fact that it is applied among a very small area.
Compressive force. Area times pressure is 850 pounds. What's the whole thickness you said?
Yeah.
Is that a single ply or is that?
That's a single ply. And our 10. So it'll be 2 millimeters, 0.2 centimeters is the wall thickness.
Oh, and the open rocket does account for if it was 0.22 millimeters instead of, or if it was 22 millimeters. Right?
2.2.
2.2 millimeters, yeah.
And
it, the ones on our graph, we're using the 2.2 assuming our manufacturing, we were able to get it to be 2.2. And we also tested with what we started with was 2 millimeters, but that was, we weren't able to reach that using this manufacturing method that we're using, 0.2. It only dropped the altitude by about like 100 feet, I think.
Yeah. This isn't unidirectional prepreg, right?
It's a woven twill, 42% resin content, 50-inch diameter, or not diameter, length roll, and then it's 24 yards.
Are you guys doing anything? What direction are your layers going to be in? Like, is it all going to be like your block like this, or are you gonna do 45, 90, 45, 90?
The fabric is a twill, so that it's manufactured at a 45-degree woven angle. I haven't gotten into the details of how I want to necessarily lay that up over the body tubes. That is again something that I want to consider further after CDR.
Yeah, I'm not the composite person, but I know that is a thing that is done.
Yeah.
Where you like can with your lays to be in different directions so you can carry different stresses.
Yes. That's the difference between a plain and a twill woven material. So plain is at a 90-degree and then twill is at a 45. So and then uni would just be all one direction. So I chose to do woven in case.
Is this mostly compression?
Better finish your sentence. Just do because.
Oh, 12 because assuming so if we assume that our angle of attack is perfectly vertical, which it probably won't be, our loads hypothetically would only be in one direction, but the twill would at least with the 45-degree angles. If we do end up not having a perfectly vertical angle of attack, it does give us material strength in those other directions. And yeah, and then your question was
Terminating load is shear or compression? Like, do you actually get much shear forces coming out of it?
I haven't necessarily considered it all that much. Like I said, I wanted to do more stress and strength analysis after CDR.
And if you're dealing with a composite, it's in compression, it doesn't matter. Compression is taken by things, not the effectors.
If you're into your compression, but if you have a mass up at the top and a force at the bottom and you start wobbling, you're gonna get tension on one side.
I guess I'm not quite sure what the question is. Do you mind just elaborating
Yeah,
on?
you need to understand what loads are actually acting.
Right.
You have a compressive loads from pressure distributed to and then you're gonna have some side loads coming from somewhere.
Sure. I
Those could be your shear forces.
I don't have those numbers.
Somebody should figure it out.
Yeah.
I have a quick thing. This was chosen because we're specifically looking for something that's shear modulus and fit into our flutter boundary equation as well. That's another consideration we're looking at because the flutter boundary equation used the shear modulus, and like we said, that was one of the primary things that adjusted how much speed it could handle. So that's kind of why this value was chosen, taking both into account, compressive and shear. But yeah, I don't think we.
And then moving on to the fiberglass prepregs in the aramid core. So the fiberglass is using the same resin system, but is a different fabric. So it is a fiberglass. Give me 1 second. Fiberglass prepreg, also a twill woven material, compressive strength of 70 KSI. So not as much compressive strength as the carbon fiber, and a cured single ply thickness of 0.74 millimeters. And then for the honeycomb core, this was the only material so far that isn't going to be donated. I can't find a ton of mechanical data on this, so this is where testing will come into play with the fins, doing small scale layups and then testing the mechanical properties of the honeycomb core. But the thickness of it is the 1.5 millimeters. Cell size is 3.175 millimeters, and then 28.83 kilograms per meters cubed per density.
So how do you make it rounded edges on mechanical?
It'll be a sandwich layup. So the honeycomb will be in the middle with the carbon fiber laid up over top, and then probably wrapped around the edges as well, and then epoxy over the edges, sanded to make the rounded edge for the fins. And then a manufacturing overview, as I included the ply thickness earlier. So our target thickness for the fins is 5 millimeters plus or minus half a millimeter. So that will be the carbon fiber prepreg with the honeycomb core in the sandwich layup. One layer of the honeycomb core, and then I believe it was 8 total plies of the carbon fiber on each side, with one of the tech variant of the carbon fiber over top to ensure a good surface finish. And then, oh, it's fine, sorry, I didn't see that. And then for the avionics body tube, that is the body tube that will be fiberglass because the avionics bay is transmitting RF signals, and RF signals do not go through carbon fiber. So that is why we're using the fiberglass for that body tube alone. The reason we're not using it for the rest of the rocket is, generally speaking, carbon fiber is stronger than fiberglass. And then for the nose cone, bow tail, and the other two body tubes, our target thickness is 2 millimeters plus or minus half a millimeter. And that will be carbon fiber prepreg, 10 plies total, 8 of which will be just the 5201 regular. And then the first ply and last ply will be the 5201 tech. Cameron?
5 millimeters is really thin. That's like 200 thou. So is there, I didn't catch it maybe, but is the honeycomb actually that thin? Like I know last year our plates were definitely thicker than that. They were
The honeycomb is about a millimeter and a half.
Okay.
In
So
thickness.
it's a pretty thin honeycomb.
Yeah.
Okay.
So
Is it just one layer of honeycomb?
yeah, I haven't thought about doing two, but that is something that we could consider as well. That would probably come into play more with testing and seeing if 1 or 2 layers it provides better strength data.
Because we can also get thicker honeycombs as well.
Yeah.
Well, I was just curious because that seemed really thin compared to, I think last year, I'm trying to think what it was last year. It was definitely.
I think it was
Closer to quarter of 300 thou,
The
somewhere
plate
around there, and that was
in the
just solid
yeah.
carbon fiber. There was no honeycomb in that.
Yeah.
But I mean, the honeycomb will allow for much greater shear stiffness.
Yeah.
compared with- So that's the other thing to consider with the honeycomb compared to the solid carbon fiber plate.
What was last year's rocket? 10K as well?
No, it's
5K.
Okay.
And then a little bit more about the manufacturing process. So the composite materials will be cured with a vacuum bag and oven cure instead of an autoclave. This is because the materials that we selected are specifically designed for vacuum bag processing. And so just a little bit about the vacuum bagging processes or the vacuum bagging process. You create your laminate by layering your prepreg and then you debulk, and that is when you put the laminate under vacuum. And when you put it under vacuum, it depends on the instructions of the technical data sheet. But for a debulk, you can put it under heat, but you don't necessarily have to. A debulk is more to just create maximum bonding between your layers and make sure that your laminate is dense and fully bonded. And after debulk, you oven cure according to whatever recommended cure cycle is provided on your material data sheet to heat up the resin and then have the resin flow throughout the material. And then depending on which cure cycle you do choose, will also determine how well your resin flows and ensure how consistent your mechanical properties are throughout your material. And I haven't selected a cure cycle yet. I do plan on talking to a representative of the company that plans to sponsor us to help pick the right cure cycle for our needs. Because I couldn't necessarily find a whole lot of information on what cure cycles produce the best results for surface finish and then even resin flow as well.
I know nothing about this, so this might be a stupid question.
No, it's okay.
But do you need like a special oven, or is this just like somebody's kitchen? Or
It's just an oven.
okay,
That's kind of like the autoclave would be like the special oven.
There's an oven that could fit probably like 20 people in it down the first floor.
Yeah.
Big enough, bottom line, big enough to
Yeah.
do any layup that we would do.
So it's just an oven, and then you have, I'll show a picture in the next slide of just how you create that vacuum bag and how your laminate goes with like different materials on top. I'll explain it in a second.
Just to be more explicit, do we have permission by the oven owner to use said oven?
Yeah, probably. I could get. Okay, yes, I just need to talk to Deltory.
Okay.
But yeah, we've used it in the past, and I don't think there will be much of an issue as long as it's not interrupting this class.
Cool.
Oh wait, actually, yeah, Austin Jasper was wait, so maybe you might know Austin. All right, he was on the fact that if y'all like really can't figure out where to do it, you can probably have him pull some triggers. He was one that was also.
And then I found this infographic really helpful when I was first kind of researching this process. So for a typical vacuum bag layup, you'll have your mold and then your laminate, so your composite material laminate with we're gonna use a perforated release film because that's what's instructed by the technical data sheet. That goes over top your layup, and then you have you can use a peel ply underneath that if you are trying to do like a consistent rougher surface finish. I have a peel ply in mind in case we do decide to use that later. But if not, then we won't order it. And then on top of that is your breather material, and that's just like when I felt it, it's glorified felt. It's just really thick, kind of a cotton material to absorb any resin that comes up through the release film. And then over top of all that is your vacuum bagging film, which is sealed around your part with seal tape. You draw it under vacuum, and then you can manipulate the bagging material to fit your part geometries and ensure proper resin flow and a good cure. These are just the specific products that I have in mind, all provided by Aerovac. And yeah, like I said, these materials are just laid over your laminate to ensure proper resin flow and maximize your final product. And a note on molds. We will go into molds later in the presentation. Just a couple of treatments that I have in mind for the molds, because aluminum and carbon fiber are at risk for galvanic corrosion. There are products out there to chemically seal the mold and also to coat the mold to help your part come off of the mold easier. I do have specific products in mind that a company would be willing to donate. And right now, the plan is to do an aluminum mandrel for the body tubes and the boat tail. We have a couple different options for the nose cone. And for fins, we would just do the layups and then cut it on the water jet or tile cutter. And then do our post-manufacturing operations to create the rounded edge. And a little bit about our... Either make one or buy one. Yeah. That is still.
We'll talk more about that.
Yeah. Most likely buy, but that's still a little bit in the air. And then for our next steps, I didn't put it on here, but testing the shear and the stress and strain on our rocket and testing that with our materials that we've selected is definitely in my next steps. I need to research more about how to go about that because I don't have a super clear plan in mind. For the surface finish, as I said earlier, testing small patches, following our intended layer procedure, and then testing that with a gauge, and then also testing our final product is how I intend to test our surface finish. And then I also, for next steps, would like to create a detailed manufacturing procedure. So just every little detail of the manufacturing process outlined in a document so we can reference it and then also look at it in future years. And then with that would be the manufacturing schedule. So just a timeline of our layups and part completion. I also would like to get a representative from one of the companies sponsoring us to come and help us with the layups, just give us their professional opinion on how to make sure that we have our parts come out as we intend.
Chat with like formula they use to grade all the time.
Okay.
So they have a lot of like historical like generational knowledge there.
Yeah.
I would recommend doing that before reaching out to me.
Okay. Thank you. And that is pretty much all I have. Are there any leftover questions for either me? I'm sorry?
We can have a separate structured section.
Can you just like step back and explain why you go and which
The honeycomb was less expensive than the solid carbon fiber sheet, as well as if we were to just do solid layers of the carbon fiber we have selected, it would be about 30 plies. And so to help increase our thickness and also reinforce the shear of our fins, we wanted to use an aramid honeycomb to help reinforce the fin material.
You're supposed to have a very big piles, carbon plates. And I can't remember the figures, but pretty reasonable.
None of them are big enough. We checked. Yeah.
Yeah, they were also, I measured them up at the hanger and they were thicker than our total targeted like fin thickness as well.
And what drives your rocket damper? Like why did you think like that?
We did talk about that more in PDR. I don't remember off the top of my head if aerodynamics
The
says.
CubeSat.
Yeah.
That's to be big enough for CubeSat.
What for use that whole 500. Like,
You usually find that dealing with different diameters depends on how you manufacture things. It'd be challenging. Like, for example, at some point we banned by designing anything that within 4 and 6 inch diameter. Basically, it was very challenging to work with TL with anything in that range because you have to flip the jaws, but then have to grab like the second jaw instead of jaws instead of the outside one. For those specific range of diameters. So like basically you don't make that anything in the middle, you can make it a bit smaller because you don't have to flip the jaw.
Yeah.
Or you can just make anything bigger because you can just flip the jaws and flip the outside instead. 7.5 sounds like it might run into issues. Another thing, like if you're looking to purchase whatever you're gonna wrap the tube around, the easiest solution is a PVC pipe. Works every time, all the time. For easy, just super awesome.
but for the like 3-inch certs that we did, it was okay. But like once you start to get 7.5, like the dimensional tolerances for PVC will allow you to like.
They made a 12-inch tube.
How did that go? Like trying to pull it off. We've had so many that like. We've had so many that got stuck just because your dimensional tolerances don't allow one
If
thing.
people get stuck and there are challenges with that, it's easier or better to go on for metal pipe, which we had the metal pipe that we used. Yeah, 9.
Yeah.
I think it was 9. So it was like we had that tube sitting there. And the solution for PVC pipe that was challenging was to feed before you put it down. And I mean, we had some issues, but the issues came from people not doing it properly. Like if you lubricate the pipe ahead of time and you put a protective layer over it nicely and don't have ripples in it when you roll it, you don't actually have much challenges. Some tubes came out with it, some tubes didn't. It wasn't a problem with PVC pipe for me.
I think the problem with PVC is it'll melt in the oven if we're using pre-preg, right?
Yeah, what's the temperature of the oven?
That depends on our cure cycle. If we opt for a longer cure cycle, it could be 180 Fahrenheit at 3 hours, 160 for 8 hours, or you could go up to 400 if you want to cure it in less than an hour. But like I said, I need to talk to somebody to see which cure profile.
Limit on that oven because the floor, it's some weird thing with like it'll just start destroying the floor if you cook it up.
Yeah, I was
oven.
opting for one of the lower and
I
longer.
think 400 might be near the upper limit.
Yeah.
Before you start cooking the floor.
I had in mind the 2 on the lower end, just because I think from the little that I could find on the differences in cure cycle, doing a lower temperature for longer can help your resin flow more evenly and then ensure like consistent mechanical properties throughout your material.
And you touched on it very briefly in the beginning. Can you explain again why we're using pre-preg and what?
Ease of manufacturability was the primary reason.
Like anybody here has done that plan?
Yeah, it's way easier. Pre-preg is night and day. It's so much easier, so much cleaner,
right? Like
so much consistent.
I personally rolled like more than 20 tubes. Layout. It's not actually challenging.
We also didn't have any super complex part geometries or like specific needs for different resin content than what is standard provided standardly. So like between the 38 and 42%, we didn't necessarily need anything outside that range. And usually for wet layups, from what I saw online, is you use wet layups when you have a more complex part geometry because a fabric that's not pre-impregnated with resin is easier to sort of like fit into complex molds, but our parts are large enough and round enough to where pre-preg just seems like an easier option for manufacturability.
Yeah. Also like consistency for your material
Yeah.
properties. Like the way that we would do our wet layups is like like wrapping the dry cloth and like pouring and then like scraping off the extra epoxy. And then it's like you kind of have to fucking eyeball how much epoxy is left in there instead of knowing like exactly
Yeah.
2%.
Exactly.
Another less scientific reason is we have connections at composites companies where we can get this stuff supplied. So even though CPSS has materials already for wet layups, because we're able to get materials to do pre-preg without having to like invest the club's money in getting that infrastructure ready for it.
No,
We
that's
felt-
what I was looking
Yeah.
So they're not paying anything.
Not other than for the mandrels and for some of the.
The honeycomb.
Yeah.
Everything you said before made zero sense. That,
About the nose cone, are we doing about that for that, or is that also gonna be pre-preg?
Pre-preg. That will likely involve cutting the pre-preg into strips and laying it up.
Yeah, like you can do a bunch of bores where it's like they can flatten it, so but then you have to like make sure that your bores line up correctly.
Yeah.
Like,
That is the part that I said I wanted to create a more detailed manufacturing plan. That is probably the biggest thing I want to look at for that detailed manufacturing plan is how to lay up the pre-preg on like for the nose cone. And that is all I have. So
What are you using for molds for the nose cone and bow tail?
We'll talk about it. Yeah, I'll talk about that. Yeah, so we'll just continue on just to make sure you're good.
okay. Structures and recovery. Thank you guys.
yeah. Wait, how many groups are there? Sorry, we've been taking a lot of time. Yeah.
I think, oh, and manufacturing, from manufacturing short, that's like short.
But are the most involved in terms of analysis and because that's the biggest biggest point earner. So a lot of effort has gone into, especially if we don't have control systems.
We'll see about that. Can't turn points in your structure crumble.
Yeah.
Okay, so I'm Ariel, this is Will, and then Cameron will also be up here later. But so for I wanted to do kind of an overview of how, like, what we're going to talk about. So for our objectives, we're going to be designing and successfully building a structure that stays intact throughout the entire flight. We're going to ensure that the subsystems are integrated in a way that makes for easy assembly. We're going to successfully utilize a dual deployment recovery system and safely recover the rocket. And then so for our main updates from PDR, so like changes we made or stuff we wanted to do after getting feedback from that. We wanted to show how plans better fit the requirements for FAR. So you'll see like on each of the slides, we have a little section of a table in the corner. That's going to be the requirement for each, or how each section fits the requirement. We wanted better reasoning for our design choices, an explained plan for integration, explained launch structure, better analysis of the parachutes and the deployment, better understanding of the O-rings, which is kind of on me, and how I didn't understand it as well last time. Weight estimate, completed testing procedures, CAD and manufacturing, and then a cost estimate.
So sequence of events for structures, we're going to be covering launch structure and how we're planning on putting it onto the rail and all that. And then motor mount, and how the motor mount's going to integrate with the fins, the fintegration, if you will. Then couplers, and then for recovery, it's going to cover the outer design, which is integration and pressure calcs, and then inner components of the drogue chute, main chute, pyrotechnic testing and parachute analysis, cover altimeter choice, and then go over the build materials. Starting off with structures. So doing the launch structure, FAR provides us with the 10-foot launch rail with that is a 1-inch width with a 1/4-inch T-slot. And so they FAR recommends these Apogee standard rail buttons, really cheap, you can get them pretty easily. They're recommended to straddle the center of gravity, with one of them being as low as possible, so that way the rocket is guided on the rail for as long as possible, and the other one being somewhere above the center of gravity. So it's not like lopsided. These rail buttons need to be in a straight line in the rocket. So we're going, when the whole airframe is connected, or at least the two segments on which the rail buttons will be placed are connected, just place it on level table and then use a laser level and drill 2 holes. And once we get the actual rail buttons, the inner diameter of the rail button, you see the mouse now. This inner diameter is not listed, but I'd also like to measure that and make sure that once the holes are drilled, that basically the difference between the T-slot and the inner diameter won't cause any like torque, like it won't have to be press fit into the rail when we put it in on launch day. So I guess
for traveling the center of gravity, at what point in time did you look at the center of gravity?
I looked at it when you
like as you go to like motor, it'll be at one location, and as you burn mass, you'll lose mass from that. So it'll shift.
Oh, I see what you're saying. Just on launch, so before like when it's sitting on the rail and then during burn. I haven't considered how that changes as it's going off the rail. Because once it leaves the rail, it doesn't matter.
Yeah, so like the mega conservative way of looking at it, it's looking at where the center of gravity is if you have no grain, or like after you're done burning your tires.
Right.
And then just making sure about that.
Yeah. Okay. Yeah, that makes sense.
Oh, great story about these buttons.
Oh no.
We were trying to launch something from far. You showed up there, you were like super stoked and ready to rocket that we can hook our rocket to the rail, no problem. Only to discover that the rail bottom diameter is too large. So Daniel had to go and turn it down on the lathe that they have in one of the sequence that sits apart. Actually has a lathe inside. If you were just running to those guys, they might have been approached. So I had to figure out a way to verify it actually fits like that.
Right. Okay.
Don't just trust this.
Yeah, and I mean they are relatively cheap, so we could always like
You can also grab a bunch and
get a bunch and just make it variable. Yeah.
Yeah, I mean, I think the I was gonna say use 80/20 and see if that works.
There was some sort of weird situation with the rail where you had to use it there.
Did you have to get moved to a bigger rail or different? Because there's 2 sets. Because I think the big thing is that there's 2 10-foot rails that each use different ones. I think one 10-foot rail uses the smaller diameter, one uses the bigger diameter.
I don't remember.
Oh wait, no, it's 1/4 inch, isn't it? Like
the new one so that one is the 1/4 inch, but for the 20-foot rail, I think
it was 5/16
or 5/16 or something like that. So there are 2 differences, but it's
well. The moral of my story is really you should go through a mental exercise of all the hardware that you can interface with that you don't own,
right?
Which is rails and complex one,
right?
And make sure that whatever interfaces you have, you're confident they're going to fit. And if you suspect they might not for some reason, have a backup plan.
Okay.
I mean, turning something on the lathe 30 minutes before launch is a solid backup plan.
Right. Okay. Cool. All right. Motor mount design. So we're planning on purchasing a paper motor tube from Apogee Rockets, and then having 4 plywood centering rings. The lowest one will be very small compared to the other 3 because it's going to be at near the bottom of the boat tail once we put the boat tail on. And it's going to have an aluminum motor cap and aluminum bulkhead. And so the fins are planned to basically slot into the centering rings. And then if we want to finalize it, we just epoxy them in. And then there will be slots in the body tube segment that allow it to basically be slid in from the bottom. And so
do you plan to have like a way? How do you plan to make sure that the fins are actually vertical?
Like vertically aligned.
Yeah.
Basically cut the make sure those are just like at perfect 90-degree angles, and then we just have to line up top and bottom. So when it slides in, it's vertical.
You definitely experiment that might work just fine. You might run a situation when there's like too much slope on one of them, or you like rotate one ring relative to each other, which gives the whole thing slight twist.
Right.
You might end up having to make sort of a jig to ensure that the pins are vertical.
Yeah.
It would really depend on like the clearance, like the basically how much wider your slots are relative to the bits of the pin. Just be mindful of that.
Yeah.
Might prove yourself to be a little more challenging.
Okay. Yeah. We'll pay close attention to that.
And how are you separating? So those slots are good. Also the way you're gonna ensure that there is a 90 degree separation between this.
Yeah, so that would also just be another basically a jig where we put it in, we cut a line through, and then we just have to make sure it's a very good 90-degree rotation before we cut the next slot, and then 90 degrees, next slot, 90 degrees, next slot.
Maybe this is my return PDR to why 4 pins versus 3 or 5 or 6 or 8.
I think that was covered. Yeah.
Right, but like, is that assuming a constant area? Because if you assume a constant pin, then as you add number of pins, it'll always increase your stability because it'll keep shifting your center pressure back. Like, the real way to do it is like normalizing based off of an area. So it's like 3 pins with slightly larger or 4 pins with slightly smaller, such that their total area is the same.
Oh, yeah, it was stability and apogee. We tried 3 pins. If we were to make the pins, or for the stability to reach what it is 4 pins, it would be way bigger. And then the apogee was just better with 4 pins compared to the math. These pins are already kind of big though. They stick out about 8 inches. Yeah, from the height.
Very good. And then also like manufacturing when for going from 3 to 4.
It shouldn't be too much work because if we're already making 1, it's just the same problem.
Yeah, I'm just meaning like in terms of making your jig or whatever, it's easier to have it be 180 and 180 instead of like having to do 120, 120, 120.
Yeah.
Like because right now you're talking about like how you're gonna rotate it 90
Yeah,
degrees.
just do.
Like
Yeah.
if you have to do 3 rotations, each one of those is gonna have tolerance. Whereas if you do
Oh yeah, I see what you're saying. Do 1 straight cut and then
1 tolerance,
90 and then yeah. That makes sense. Cool. Yeah, and so then for putting the boat tail onto it, I'm gonna go over to this side so I can point at it. But the centering rings and the fins will be attached to the motor tube first, and then this will give us access to the motor tube. So when we get the grain, we can put it in, and then once we do that, these will be screwed in with nuts up here into L brackets. And then we'll put the boat tail up on it basically. And then we'll have these ones be threaded. So that way you just screw it into the sides. And we're gonna also screw it into from the bottom to the centering ring. And these will be both attached to the main tube with epoxy. And then up here, it'll be attached to the airframe segment with epoxy on the centering ring. And then yeah, just screw it in. And so that allows us to access the grain on race day, and then also like make sure that it is well connected. And there will be 4 brackets around the side, and then 4 screws around the bottom.
race day.
Race day. Sorry, I rode in high school like 2 hours. So I'm like, all right, it's race day, launch day.
So can you explain the beginning of the process again?
Yeah.
Brackets, what are the L brackets and how are they attached?
So L brackets will be attached through. There will be 4 of them. Circular, and there will be attached into the centering ring up here, and they'll be screwed in and then have a nut and washer on the top.
Probably. The L brackets are in fact attached to the center ring.
Yeah.
They don't get attached to the tubes.
Yeah, that's your shear.
Yeah.
It's like center ring and an L bracket, and then that's how you carry shear from the boat tail.
Can you explain how the actual motor mount assembly is then also going?
Oh yeah,
because I think that'll help clarify.
Yeah, and then
we're using it through the wall today.
What?
We're using it through the wall construction.
Yeah.
So
yeah. discussing it. But yeah, and then the whole motor mount is going to be put into the body tube segment, and then it'll be. Yeah.
The nut goes on the top of the ring.
Yeah.
How are you getting
Are you going to go back a slide?
the body tube, I guess?
Yeah, so this is what it'll look like when we're like putting the bracket in.
Okay.
So we'll have very easy access to
Okay.
the top of this.
Yeah, and then that whole assembly is shuttled in.
Yeah.
Wait, so all your bulkheads are aluminum, right?
Yeah, and that's on the next slide.
How thick is that rear bulkhead? The one like just after your pin?
That'll be next slide. Do you know off the top of your head?
I haven't looked at the bulkheads too much.
Okay.
I think that's still up in the air because we're trying to determine whether it's worth it to, I'll talk about it.
Next slide.
It's still up in the air.
I think
Based on
the people like Alex, like you don't need to add L rack, you can just tap your bulkhead directly. Right, just screw into that.
Yeah. Okay. So yeah. Cameron. Okay, come off.
Okay. All right. So yeah. For this rocket, there's going to be 3 couplers. 2 will be on the pressure vessel. So the first one is the pressure vessel and the nose cone. There'll be an O-ring on the pressure vessel side. I'll talk more specifically about the pressure vessel a little bit later. The bottom one is pressure vessel avionics, again, O-ring. So those will be sealed. It will be kind of similar to last year's coupler, where it was a solid billet and there's going to be a sealed section in the middle. The one that's the avionics of the motor will be a hollow tube, just a lip. Right now, so we looked at doing a bending analysis. I still need to look at buckling. We haven't done that, but I talked with Nick Powers, who's a civil and knows a lot more about the bending stuff than I do, and he talked to either Casper or Hall, whenever one of the CE204 professors I'm sure you all had, and they basically determined that doing an analysis on bending is probably not required because it goes higher order really quick if you do hollow tube. So hollow tube bending is really weird because you have like both tension and compression on both sides. So they kind of just realized it was probably not necessary. So we're going with pretty much around 3 inches, 75 millimeters. I think last year we had 2.5 inches for like these lengths, and it held up fine. So between that and there's going to be 4 screws on each one. The screws, we're still determining whether there's going to be a through hole on the coupler and then it's going to thread into the bulkheads, or we're going to thread these, make these threaded, and then actually thread the bulkheads in by doing a huge thread. I think that we'll probably end up threading the bulkheads and doing a through hole on those, just because that's a lot easier to manufacture than having to turn a huge thread.
All right, I'm gonna go back to the like it was 2.5 years or 2.5 inches last year and it worked fine. Like you guys are working into very different flight regimes. Like
yeah,
you're going twice the velocity, so you're going to be going faster, which means your dynamic pressure is going to scale more.
Yeah,
and then you're going to get a moment on it trying to bend the rocket.
Yeah,
like I think we should look into.
We'll look into it. Yeah, and so I also one of the things was that I did edge shearing calculations and like bolt shearing calculations, more specifically for the pressure vessel.
Yeah.
But the safety factors were like so large in those that I was like, I don't really think like it would need a lot of force in bending to actually do something.
Yeah, I mean, it like is dependent on what the shear force is that you're applying onto it. That's actually causing bending on it, right?
Yeah.
Like, that'll be probably dependent on like if you get a huge gust of wind.
Yeah. So it's still something that we may look into, but just based off of the safety factors I got when I was doing pressure vessel calcs, we kind of determined that it was likely overkill to do, because the approximation we were looking at would have treated it like solid anyways and not been like a hollow body bending calculation. And at that point, then we were kind of like, well, you're not really, it's deviating very far from what it originally was compared to if you were to do like a hollow tube calculation. So we were like, it's
superposition, all the same. Do you have a cross section of this? I don't think I'm visualizing.
No, I can draw it though.
It's like straight up just to the cylinder.
It's pretty much, yeah. So it's basically, I guess there's more space over here. So this is like the cut.
You can just fill it, and like if this is actually just a cylinder, you probably just want to make it out of tube or pipe.
Yeah, so we will make this one out of pipe, because you can just buy thicker rolled pipe, and so it pretty much just look like this. If this is like a cut view in half, that would be like the lower one because it doesn't need to contain any pressure or anything between like the avionics and the motor. And then the ones where there is a pressure vessel, unfortunately, do have this section in the middle. So that's going to be like CNC weight reduction. I'll talk about that more in manufacturing specifically.
Why do you have this like H cross section?
That's because there's a pressure vessel on this side, so this needs to actually like contain pressure. Like this is like one of the walls of the pressure vessel, basically.
Would it be possible then to do some sort of insert in there instead of making it out of one?
So yeah, we thought about that. Basically doing it out of a tube, and then let's say like welding something in place or threading something in place. Either way, I think welding for kind of if you want it super thin, the welding will definitely warp and just be a bit more of a process. Like I think it's fine. I'm more comfortable personally just like running it on a CNC and doing weight reduction, even though that's like kind of janky.
I mean, but also in terms of material cost.
There we go. Yeah, that is true.
Like, what about something like taking some of the carbon fiber plate that we have and stacking that up and using just a boatload of epoxy?
Or is there a better way?
Or a better way?
Okay, welding is the way you'd want to do it, right? Like you would want to make this and then do like fillet welds there.
If you're worried about water, you can turn the outside diameter after the weld.
Yeah, that was one thing we were considering too.
I mean,
so.
Yeah, I think like what you could do alternatively is like, yeah, here's your base stock, right?
Yeah.
Right, so you like cut here, cut this out.
Yeah, that's what we're doing for the avionics one.
Yeah, and then you can
thick wall tubing.
You can like cut here such that you leave like a shelf here and then put a plate in.
Okay, yeah.
And then like epoxy this here with like high sol or something. Because like if you're applying force here, like you don't really want epoxy to carry your shear.
Yeah.
But this allows you to carry shear across the interface.
Okay. Yeah.
And it's like you'll still get a decent amount of strength.
Yeah, that's definitely something I hadn't really looked into. That would make life probably a lot easier doing that, not having to run the weight reduction program like we did last year. So it's definitely something we'll investigate further.
Because even last year, that coupler was still incredibly heavy and.
Yeah, because the reason that was heavy was because the end mill length of cut we had was a lot shorter than like there was a lot. This section was not very reduced. Like it was reduced as much as we could with like a 2-inch length of cut end mill or whatever it was. But like in this scenario, we would probably buy a end mill with a reduced shank and do it in like actual steps and actually like do the correct programming instead of me doing it in 5 minutes. And yeah, it was pretty bad. So yeah.
So what was the lot? Okay, then that was
5
It
inches.
was like 6, I think.
Or was it like, or 5.5?
So your L over D is improving by 5 millimeters. So, right?
Yeah, I think so. Yeah.
You're fine.
Yeah. Well,
How much?
like that was the thing. We were kind of like, if we wanted to optimize it, we were like, well, we could just go conservative and make it bigger. Yeah. So that's that. And then yeah, now we'll talk a bit more about the pressure vessel stuff. So yeah, like we said earlier, it's gonna be housed in a carbon fiber pressure vessel, will be turned on the same mandrel or laid up on the same mandrel that the body tubes will be laid up on. And then the couplers, as you can see here, have O-ring grooves. So those are sourced from a Parker O-ring manual and should just be able to be purchased. I think we have a purchase link that we dug up. So yeah, and then these, you can see these sections have they're drilled for the CO2. They're still not finalized, so we can still move stuff around. The location of all that stuff isn't crazy critical right now. And like you said, I think we should definitely look into turning an inside lip and laying a plate up as opposed to doing this out of solid, as it would make life a lot easier. For the pressure vessel, as a fail-safe, we're gonna have 2 pin-sized holes drilled on either side of the body. We do need to do testing to see whether they'll actually disrupt the pressure vessel, because in theory, it should pressurize quick and then burst the shear pins that are on the end. And then these pin-sized holes are just for a fail-safe in case some reason it pressurizes but doesn't actually fail. It won't be like a bomb basically when it lands. So that's that. The body tube length is 30 centimeters right now. The diameter is 19.4 centimeters. Again, same as the actual body tubes of the rocket. They're going to be laid up on the same mandrel. Yeah, so that's that.
The reason you calculate the vessel is because you need to pressurize volume to CO2 to pop it.
Yeah, to pop the nose cone off. To deploy the parachute. I don't know. Yeah.
What material are you using your screws?
They're screws. They're like nylon screws. I don't know. I'll show the next slide shows some calculations. Like I did a little script that calculates a bunch of different stuff. So yeah, this kind of just illustrates how it all goes together. We're using M6 bolts. I think my script is still for M4, so the safety factors will probably be even higher. And then yeah, like I said earlier, O-rings will stop a leak. These will need to be custom ground, so I'll talk more about that in manufacturing. Probably be done. Well, I mean, in theory, if you're following the manual, we'll see how it ends up actually playing out. But they do provide a profile.
Like recommends a certain surface finish.
They provide like a profile thing. I don't know. We can give it a shot with the high speed like form tool. We'll see. Who knows how it works? So this is by the script that I wrote. The whole code is somewhere in one of the channels. I think in structures and recovery or in the appendix. You actually want to look through it. But it basically just takes a bunch of things and it's pretty parameterized. So you can play with a lot of the settings, including like length, number of pins, and the amount of CO2. I just checked the altitude pressure change just because I didn't have a good feel for it at the time. As you can see, it's like 300,000. So I didn't need to actually do that. The stainless steel bolt yielding is the lowest one, but there's no case where the stainless steel bolts will yield. 4 stainless steel bolts will yield before 3 nylon bolts yield. So
I just stainless bolts. Can you go back to it?
Hmm?
Can you go back like 1 or 2 slides where it's
I don't know if they're modeled in, but they would just be like in this, like perpendicular.
Yeah, what are they?
Not on the side that's failing. I guess this would be the side. The nylon bolts would be up on that side. So it'd be.
What are the stainless bolts actually like fastening?
They're fastening into the coupler, so it'd be a through hole in the body tube, and they'd be fastened onto the coupler.
Oh, they're attaching body tube to the coupler.
Yeah. Mm-hmm. Yeah.
And then did you like? Sorry, go 1 slide forward.
Yeah, so the nylon bolts, obviously, they should be a fraction, and it's a pretty small fraction, so they should fail no problem. I also checked edge shearing, since that's sometimes a problem. So that's basically this, where the bolts don't fail, but it rips the carbon fiber out. As you can see, 28 is a pretty good safety factor. I don't think we're gonna have any problem with edge shearing, and that also kind of played into the role of like not thinking about the bending calcs too much, because that was like a pretty high number. And then for the actual pressure vessel calculation, we used a brittle Coulomb-Moore approximation because again, it's like a brittle material. And as you can see, 341 is the safety factor we got. So I'm not very worried about that actually failing at all.
What's the brittle material that you're talking about?
Carbon fiber.
Okay.
Yeah. So
and then for the nylon, you're talking about them yielding. What yielding is going on here?
They just failing. Like
Yeah,
they
shear.
shear.
They're failing in shear.
Yeah, they're being sheared off. They're being sheared off. So the end cap, they're perpendicular to the end cap, and the pressure, it's as it pressurizes, it's just gonna.
Right, but it's like an ultimate failure, not yielding, right?
Yeah, it's ultimate failure.
Yeah.
Yeah.
So like,
right. Oh, I guess I should. Yeah. Okay. I should just read like the. Yeah.
Shear yielding. Is
Yeah. Yeah.
And then did you account for the like preload that you're gonna be putting through the nylon bolts? Like when you go to torque it, you're going to stretch it.
So no, and again, like, this is something we'll need to determine kind of experimentally. Where I actually pulled the failure values from was on whatever the site was where we're buying them off of. They just were like, we found that like this force sheared 3 bolts. So I was like, okay, well, I'll just use that for now. And that's kind of why I parameterized the whole code too, so that we can actually do testing and come back and change stuff later pretty easily. But yeah, that was definitely one of the things that we need to test to make sure that what the number they give us is pretty true, because it was literally just a little segment of like, yeah, this is the force that it takes for 3 bolts to shear. So
yeah.
Do you have a discussion of testing plan?
Yeah, I think that's a bit later.
All right, so we're gonna go into each different way that, well, the deployment of each chute. So for the drogue chute, we're gonna use 2 of Tinder Rocketry's CO2 peregrine kits. These are the CO2 canisters that Josh was talking about earlier. And you can see at the bottom a layout of how they're set up. There's a very detailed instruction manual on their website. And then we also created testing procedures, which I'll talk about later. But we're using 2 of them on either side of the eye bolt, as you saw in the other slide of the coupler. So right there, you can see on either side. And then they're just bolted in. And so the reason we're using CO2 deployment is that you want the parachute to release at apogee. And last year we faced issues with having the rocket did not reach the intended apogee. So that meant we were relying on the ejection charge of the motor to release the parachute. And so it was falling already, which we did not want. And the other reason is because CO2 is a very clean system. It doesn't damage any, like parachutes are inward of the inner components of the recovery system. So the way this works is that first the rocket's going to hit apogee. The altimeter is going to sense that the velocity is 0 meters per second. And it's going to send 0.75 amps of current to the EMATCH and the CO2 canisters. The CO2 is going to be released and it's going to flood the pressure vessel, and the pressure vessel lid is going to separate. Yes.
And how are avionics going to connect to these? I'm guessing just a positive and negative leads.
Yeah, there's also going to be another slide on altimeters. So for our main chute deployment, we're using tender descenders, also from Tinder Rocketry. We're also using 2 of them because we want redundancy. These are going to be attached between the shock cord, between the eye bolt and the quick link. There in the appendix, there's a layout of how everything is set up. I didn't want to put it on the slide because it's a little bit confusing because there's a lot of connections and a lot of shock cord. But our reasoning for using these is that there's a very wide range of resources available compared to the perm, which there's very few resources on the internet for that. They're one of the most commonly used methods, and people really enjoy using them because they're easy. The lid just pops off once the charge goes through. And we already have one of them in the CPSS cage. So for our sequence of events, for the tender descenders, the altimeter is going to read an altitude of 1,000 feet. It's going to send 0.75 amps to the EMATCH. The black powder in the tender descenders is going to cause the housing, so the bottom part right there, that is going to lift up. The quick links are going to separate, and the connection preventing the drogue from pulling out the main chute is going to be broken, and the main chute is going to be released. Okay, so for our altimeter selection, we worked with avionics to come up with the right altimeters and how we're going to lay it all out. But we're using 2 COTS Perfect Flight Stratologger CF boards. And these, it's a long title, but we're going to be connecting all 4 of the devices that need current to each altimeter. And this is for redundancy. These are also the FAR recommended altimeters. They can be programmed to sense velocity and change and height. So we're going to set one of them to sense the negative velocity and the other to sense the height. These use standard 9-volt alkaline batteries, and the battery is compatible with the chosen EMATCH. A lot of them, we really had to look into the EMATCHs because a lot of EMATCHs require 12-volt batteries, but we found these are compatible.
I have a question.
Yes.
So avionics / payloads was planning to provide power to these. We were going to be running these off of our 3 batteries. Is that still okay? Yes, we have 3 18650s wired in series.
I was not aware of that, but it would probably.
Okay, we have power for you guys as well as virtual ground, which will then be able to enable these when we pull the arming rod. So. We got you guys.
Yeah, so I guess 3 different ways it's gonna go off.
So like
ultra redundant.
So
Yeah.
no alkaline, no 9-volt Duracell batteries in the rocket. That's kind of what I'm trying to get at, or are we?
Okay.
Okay.
Yeah.
All right, perfect.
To be clear, these were still planned on being housed in the avionics
Yes,
bay.
yes.
Yes.
It is gonna go up through the pressure vessel and through a small hole that's gonna.
They're modeled into our bay in one of the slides. We can see in a while when they're represented. We would run wires to them from the power board.
So you just have like two completely parallel, right? Like,
Yes.
Yeah.
Completely separate.
Okay.
Yeah, like you said, both are completely separate from our flight computer as well.
And you said one of them was gonna be doing velocity and one of them was gonna be doing altitude, or is it doing both?
Well,
Both are doing both.
both on each of them. And so this is the hole it's gonna run the match through right here,
You're running both of the matches through there?
or for the tender descenders. And then the peregrine is gonna, the E matches are gonna go through the bottom. So they're not gonna need a way to get into the pressure vessel.
Yeah, but both of you only have one tender descender, right?
We have two tender descenders.
And are both of the like command wires for the tender descender going through that same hole?
Yes.
What if you have like some sort of common failure that like causes damage to that hole?
I guess we're gonna have to look into that. Account for that.
Just set the lines.
Yeah.
Two holes.
Okay, so for our testing procedures, I have them all laid out. They're not in the appendix because they're very long. But I have them if anyone wants to look at them. They have been completed and we're gonna do this in the propulsion laboratory with proper supervision. So the safety manager, Ryan, is gonna be with us and then we're gonna wear proper PPE. We're gonna be doing, well, I guess a total of 3 different tests, but 2 of them are gonna be tender descender tests, 1 for each. Because we want to make sure the one we have already works and then also the one we're buying. And then we're also going to be doing a pressure vessel ground test. And this is going to take place after the whole thing is already constructed. We're going to have to wait 24 hours in between setting the CO2 canister because we have to epoxy the match through the actual housing. We're also going to be using an old parachute for this. We have an 84-inch one. So we're going to put that in there to see if it actually shoots out. For the tender descender test, we can do this pretty much as soon as we get the second tender descender.
What is proper?
Like, it's all laid out in testing procedures, but like nitrile gloves, proper ways to deal with black powder, you know, face masks. Yeah.
Ear pro, eye pro.
Our safety officer looked at the thing and said it was very good.
We will
get that going first.
Okay, so
So,
yes.
Could you go back to that slide with testing of the pressure vessel? So, or maybe you have another schematic somewhere. What does your test outline actually like? How are you collecting the test?
We want to make sure that the shear pins are actually going to fail and that the lid is going to open so we don't end up having just this thing going towards Earth with no.
And are you planning to apply holes on that thing while it's being tested?
Just on the ground. We were thinking about launching it on a CERT rocket, but I don't think it's going to be complete in time to like test that altitude change.
You meant like example, we had a coupler that we was used for prong kind of thing. It was white powder actually, but the point was it actually behaves different whether it was intentional. It had this ugly thing of tension. It also used nylon bolts around circumference, but it will separate by force of black powder exploding inside the cavity circumference instead of volume, but it does not. None of like if you don't apply any load to it, it will pop and be fine.
Okay.
If you put it in tension, some nylon bolts will share and some others will.
I see. Okay.
And then your rocket will actually stay together. You will think that putting it in tension, like preloading it ahead of time, would make it better. But it actually wouldn't because it would just cause a limited load distribution between fasteners to manifest itself more, and then one of them just fading earlier and releasing all the gas before it like has time to basically control. So when you perform this test,
Mhm.
you need to think about what are your test like apply exceptions. You're doing this on the ground.
Yeah.
So load, like vehicle loading is definitely one of them. You have the scuffler that has moments and forces going through it. How would they affect performance? And then how many level books you have again?
Four
Three.
or three.
But it's 3 right now, but that's something that could very easily be changed just kind of based on testing.
What could be challenging this three is ensuring that you actually are they compressing the sorry, I forgot your slide. This is the thing. Are they compressing the board?
It should be, I don't know, it's basically just based off of Parker manuals like they recommend.
I'm just saying, like, you have, two plates sitting in the face, right?
Yeah.
Two things sitting in the face. Are they being compressed with the wood from the nuts, the bolts? Is that how it works?
The couplers?
Yeah.
The
pressure vessel.
The bolts are perpendicular to.
Is it piston seal?
To the.
No, piston. So, okay, so bolts are, got it. Okay.
Yeah. Yeah, and then I did the O-rings are based on.
So yeah, like if you have three of them, you might run a situation when they break in and even like low distribution between them.
Oh, is any like
is not safe.
Okay.
One of them opens up.
Yeah, and then it's
and then doesn't.
Yeah,
and then
Yeah, I think actually like going with the piston seal helps with that though, right?
I think.
I mean, on
Yeah,
that
like
front-
we always ran base seals, but I think piston seal's probably better.
Yeah, I talked to Mello about doing a face seal versus piston seal because the manual had both. And he was saying like this configuration is pretty much a piston seal and he wouldn't do like a flange.
Yeah, we were in a flange.
Yeah.
We were in a flange.
I don't know if it would have made much of a difference. I think they were both pretty similar, like when I was looking at the two and comparing them. But yeah, Mello was saying go with piston seal.
So yeah, that's definitely something we're gonna have to look more into and consider.
And then another thing to consider
Yeah.
would be, so you're using the steel canisters.
Mhm.
How do you fill them up or how do you run the pressure they're on?
They're
Do they come pre-charged?
yeah, the whole setup comes together. So with the vial of black powder, and actually it's not on this, I don't think, but
Or you don't have to deal with black powder yourself. It comes.
we will be getting black powder source.
Black powder?
It does not come with black powder.
No, in terms of sourcing black powder, that's something that I've talked to Cody last year. And I've been able to arrange, we should be able to get it through Cody.
But like canisters.
Yeah, it's just like the boom box.
Like there was no point in that.
Is there any black powder that the order bunker? Okay.
I would be surprised if there was. Also, it's like $20, and I'm assuming most of you are 18 years old. Just
yeah, it's not a problem.
I don't know. We went to a safety thing last year. And apparently, there's like where we were told there's a black powder shortage, and they told us to not try to make our own black powder.
Don't
There was, I know there was some difficulty.
Don't try to.
Yeah. So, but yeah, we can definitely look into where we can get black powder.
Where is it? Okay, so for the parachute analysis, this is one of the things I thought a lot about during PDR, what needs to happen to analyze these. Because for PDR, we originally had chosen different parachutes, I think 84 inches and 48 inches, with being like, oh, this is what we did last year, and that worked really well. But actually looking into it and the requirements, we ended up changing them to 30 inches and 96 inches. So just some basic recovery requirements that you see everywhere pretty much is a safe terminal velocity is around like 3 to 5 millimeters per second. So I took 4.5 meters per second to calculate like a safe diameter for the drogue and main chute. So a total of 3.05 meters was calculated with a mass, not including the motor, like once the motor's exhausted. And then the drogue should be a fourth of the main chute size, is also pretty common knowledge. It's more fourth to fifth. Which last year that was more like half, so we wanted to change that. So we chose a 0.76 meter diameter drug chute and a 2.44 meter main chute. So that's 3.2 meters total, so a little bit of access for safety. These are called the Iris Ultra Standard 30 inches and 96 diameter chutes. They have very small packing volumes that are, I calculated, they're going to definitely fit inside the pressure vessel with the shock port. They have high drag coefficients, which is why this website is really good to use. 30 chutes is where we are going to buy a lot of the recovery equipment because of they're very reliable and they cost a little bit more, but they have very high drag coefficients as well. So the estimated terminal velocity and the code is in the appendix for this as well. But it's 22.47 meters per second with the drogue chute alone. And then we have our range for the drogue and main chute because of the different drag coefficients. So that's like 4.5 to 5.36 meters per second.
Your requirement says that it should, the flight system should be recovered in a reasonable condition. Does that mean you're going to disqualify the pin break?
Sorry?
The pin snaps in half because you landed right into the pin.
The fin snap.
Oh, to fail the back.
Is that qualified? Is this
Oh, sorry.
If that's the case, that might actually be the practical pins.
But yeah, that's something I don't know. That would be. Yeah. That's something that.
Yeah.
When you guys go with like the donut designs that are just a whole, what's cool?
That's kind of their standard parachute that they have on their website. Iris Ultra. They have a bunch of different designs. This one is the most commonly used.
What is stopping you from picking larger than it? Like, why should you want to minimize it to be 96 inch?
Minimizing the cost and then also the packing volume.
Is packing volume actually a challenge?
Not right now, no. We can choose a lot. Yeah, we do have the ability to choose like 120.
5.3 meters per second is breaking your fins if you happen to land with them. And it's very easy for you to just go larger parachute.
Okay. Yeah, there's also an 120 meter or inch diameter chute. You can also choose if we want to do that. Yeah.
Do you plan to test it today?
Not.
Parachute deployment or you can throw it off the roof of something.
Yeah.
Which we
I'm
have
trying
done
to think
that
about
with
how we could test
one-
that.
Elena was our recovery lead back when I was president, and she saw parachutes. And we were actually dropping them from like the parking structure.
That actually would be a good test to add. Yeah.
So if you were like, my fin might break.
Yeah.
You might attach a representative structure that looks kind of like your, that pin support thing to your parachute, and then attach enough mass to simulate rocket mass, and then throw it at the roof and see what happens.
Yeah, that'd be a pretty simple test to do.
And then if it lands in asphalt, that's probably enveloping the surface you wouldn't count. They don't have much asphalt.
And then another thing they're considering was the snatch force, which is the force at the release of the drogue chute. So like once this thing releases, how much is it going to pull back basically? So that's only 9.69 newtons.
How did you calculate that? Because that seems really bad.
Okay, it is in the appendix. I can should I pull that
also,
up?
like, keep in mind that this isn't going to be a static force; it will be like an
Yeah.
impact load.
Okay.
So like you have a ton of uncertainty with anything dynamic like that. So
Yeah.
going down to millimeters of accuracy for like load is probably unnecessary. Like, but also like 9.7 newtons seems really low to me. It's on the order of like 2 pounds of force.
Yeah, it's
So
I
like if that was a
think about
comma
that.
instead of a period. Yeah. have bad eyesight, but
Do you want to see the,
I don't think I understand what mesh protection.
so when the drone is deployed, and the rocket's just entering negative velocity, like how much is gonna like shoot back up or
It's like the yank,
Yeah.
when the parachute comes out, it's the yank that happens.
Got it. Yeah.
do you want to see that code?
Yes.
Okay.
I think we can like,
We can do it.
yeah, we can kick that can down the road, but I am very suspect of that number.
Okay.
Also, like, keep in mind that like bam, parachute comes out, like if you're coming in at an angle, it's gonna pull up
True.
and it's gonna like give your body to, and your shock cord is gonna be like this. If you have a high enough impact load on your shock cord, it'll rip through your body.
Yeah, so we actually are getting shock cord
Yeah,
protectors.
that's what 30 dirty or whatever.
Yes.
I love the
We
30 dirty.
did a little bit. Rick told us about it and we fixed it for one place and then we didn't see it in another place and that's where it happened.
Oh, yeah.
But it didn't, yeah, it wasn't, it still recovered.
Yeah, it like
Covers.
like it's recovered and recovery like messed up your airframe.
Yeah.
There is just a jagged line down one side of it.
It's like ripped.
It can theoretically.
Yeah, there's we're
It's the shock cord's gonna be in the pressure button.
yeah,
Yeah.
and we're actually
Has to go through. Who's close?
Well, it's basically.
There's eyebolts inside.
Oh, right, so it's out and then there's the hinge and then if it's a small, high force in a small area.
Right.
Mhm.
It's gonna shear through.
I can show you the
Yeah, the development.
so
Yeah.
the shock cord protector, the flame resistant shock cord protector, we're getting 3 of them. So for each side that the shock cord is gonna come into contact with the body tube. And then we came up with a total of around $1,310-ish. This is subject to change. It also includes the avionics altimeters, which I realized like an hour ago. Avionics also included that in their bill of materials, so it's gonna be less. It doesn't include carbon fiber or the aluminum, which is gonna be sourced from composites place we're getting material from. And then it doesn't include brackets or screws.
You guys have some sort of piston for your shoe? Like usually if you have like pyrotechnic, you'll have like either piston or they call it dog bar where it's like packing material between the thing that's actually providing the thrust and your shoe, so that way you don't like damage it.
Oh.
I don't know if it's still needed for CO2.
It
Yeah,
shouldn't damage
no
it.
next sheets.
I think it's like it's something like furniture with the dog bar. Like it's foam. So that, but I think that's mostly because it's pyrotechnic.
Yeah, it's usually the flavor, because that's what we were using last year. It's just like no max fire resistant sheeting, just to protect so that your shoots don't. I think it might be useful just to transfer to just basically punch everything out, so that each go individually, but.
I'm guessing the CO2 would make it more safe, but I think adding that still would be a good idea. Okay.
This is a question for Josh or Matthew. Do we have a maximum budget for this project? And also, do we have an estimated total cost of the rocket design currently?
I have an estimated total cost and I'll go over that at the very end. I don't know about actual budget. I don't know.
I didn't have left.
Spend until somebody tells you to stop, man.
Get all our stuff ordered and then they.
Then manufacturing is next.
Yeah. I think before we actually just might just take a quick 10-minute break so that we can just clear our minds.
Can I play a game of blitz chess while we can I do some blitz chess?
Okay, getting back into it, we have Cameron with manufacturing.
All right, so I'm talking about manufacturing. It's just pretty quick and pretty simple. So yeah, I would recommend doing the lathe training. Probably is the most like the machine that's going to be used the most in terms of manual. We will be doing some mill stuff as well, just mostly like rotary vise to drill holes and indexing and stuff like that. So those are the two I would recommend. If you're interested in welding, I would go for welding. That is probably more of like a the test stand team or whatever that project is. They might need that more. But yeah, this is the website. Do your trainings if you are interested in actually participating. Although I have a feeling that a lot of manufacturing is going to be composites, which in theory, there's a composites tag in the work. Again, that will not actually be a thing probably until some point next year. So yeah, I wouldn't worry about it, but do that. So kind of a loose plan and urgency. I don't really have any dates set yet because I still need to kind of talk to everyone and figure out what needs to happen. But I know the highest priority is the mold for the body tube. So right now I'm looking at turning that on a manual lathe. I did actually go in, flip the jaws and check to make sure that it could hold 7.5 inches. So they can. We'll need to use a steady rest probably, but yeah, once that one's done, we can start doing the body tube layups, which I think will probably be the most time consuming of this whole process. So my goal is to get that done pretty early. The boat tail mold can be turned on a manual lathe as well, since that is not a compound angle, it's just like a linear angle. You can just use the miter gauge. The nose cone, so this one is the one where I'm most up in the air about. It's either going to be machined on the VF2 with the trunnion or theoretically the Aero 5-axis. The Aero 5-axis might be overkill. Plus, I would need to learn to actually program it, so I kind of want to not go that route. I am of the opinion of like 3D print and wet layup, but there's still some discourse going on there. So the nose cone still is kind of the most up in the air. The couplers will be turned on the manual lathe and then put on the mill with a rotary vise to drill holes. Again, weight reduction will probably be done on the VF2. I did it last year. It was a little bit chaotic. So I'm hoping to do it a bit more well planned out this year if we do need to do it. Although if we do end up doing this plan, that would make life a lot easier as I wouldn't have to do that step. So I'll definitely be investigating that. Right now, my plan for the O-rings is to custom grind a high-speed steel tool and just then turn it on the manual lathe. We'll see if that ends up working. I have a feeling that the profile doesn't actually need to be that precise. I think it's worth a shot just as a cool project. So if anyone is interested in custom grinding high-speed steel tools, it's not very common anymore. It used to be done a lot back in the day, but now with CNC lathes and all that, especially carbide tooling and all the inserts that are available, this is kind of not as common, but it's still something that I want to try. So if we've got time, I'll give it a shot. And then the carbon fiber fins, the plates, that doesn't really need anything besides just the ability of like knowledge of how to do a layup and maybe some space and obviously like the oven and vacuum bags. So that's more of kind of Kendall side of things. That can all be done concurrently. Really, the only thing that is kind of would cannot be done concurrently is the mold for the body tube. So that's just kind of a brief overview of what I'm aware of right now. Yeah.
You use a boat tail mold and a shot lock instead?
Probably. I just don't have ShopBot. Like I'm not certed on the ShopBot. And there's also a new ShopBot they just bought. So I don't know what the deal is. The old ShopBot is like falling apart. So there's a new ShopBot sitting there. It's in a huge bag in the back of the hangar. I don't actually know what the timeline on getting that installed is. But yeah, I mean, the boat tail could totally be done on a manual lathe. Like it's just a linear curve with the miter compound or like the. Yeah, I was thinking because if you want to do pre-preg, so the thermal coefficient of thermal expansion of aluminum is greater than the carbon fiber. So when we put that in the oven, this will also help separate the carbon fiber from the molds because the aluminum will expand faster than carbon fiber will shrink. So when you're curing, the carbon fiber is drying and it's getting expanded by the aluminum. And then once you take it out of the oven, the aluminum will shrink more than the carbon fiber does. And that should, in theory, allow for easier separation of all the components.
You're laying up on the outside or the inside?
Outside. But I could do it on the inside. I mean, I don't know. That's another thing to look into. At least for the body tube, it would be the outside. The boat tail could be done either since there's, I mean, that whole thing is a draft angle. So that'll separate, I don't think, with very much issue. So that one could be done outside or inside.
So if you're laying up on the outside of an aluminum tube with a higher coefficient thermal expansion than your carbon, like your aluminum tube is going to be this big and want to be this big, and your carbon's going to be this big and like not really care.
Yeah.
Which means that you're going to have like stresses internal.
Yeah, I don't think it's a huge. I don't think it's like that much of a disparity that it really makes a difference. Like I'll have to research it more, but that was just like one of the common things that I've come across when I was researching like pipe layups and stuff like that, or like cylindrical layups. Is it's pretty common to do that because it just I don't think it's very big, but it's enough to make separation a lot easier. But I don't think it actually is substantial enough to impart like residual stress that would like be in there after it cured.
Yeah. So the other thing I was gonna say is like you're doing boat tail mold out of balloons, like how big of a taper are you gonna have at Aerotine? Boat tails like half angle?
150 millimeters from the 190.
Gotcha. So that's like a lot of material to augment.
Yeah, I mean, it would be. I mean, it's yeah.
Would that be like? Would you start from billet for that?
Probably. I mean,
that's expensive.
Yeah, I know. So that's
7.5 8 inch diameters.
Yeah.
Expensive. I don't know if you can do it on ShopBot. I think that would be.
I mean, we could also do it with like it depends. We could do it with a different material. It just like whatever we're doing it with, we have to make sure it can withstand the or like the oven. So we could do it out of like HDP or something like that. Which I mean, that would you'd rip through that. That I don't know how expensive that is compared to aluminum, but yeah, it'll still be a lot. So I don't know. That's kind of still something we're looking into in terms of like price and actual optimizing and like trying not to spend as much. But yeah, I think the main factor in all of these is like ideally you could just, especially Botel too, like could just be 3D printed. But that would limit our access to actually doing pre-preg. So we'd have to do wet layups if we wanted to like do a 3D printed mold because the 3D print would melt in the oven. I've learned that one the hard way. So yeah, but it's kind of up in the air still, but it's definitely being considered the different methods of how we want to do it.
How long are your teams?
Okay, yeah, and then some potential issues I foresee. Obviously, the body tube is very big, so it'll need to be put on a steady rest, which I've never done, so I just got to learn how to do it. Probably a 4-jaw as well if we want to actually dial it in, because those lathes get abused and the run out on them is not great. So we just really need to dial it in before we start machining and make sure that everything is as there's as little run out as possible. Again, like also access to the Aero 5-axis machine. I kind of don't really want to use that one, but I don't know if it comes down to it, we can use that and I'll learn how to program it.
Why does it need to be 5-axis?
That's just the one they have. I mean, I just don't have okay. The problem is I'm not started on the CNC lathe. In theory, this nose cone part is the CNC lathe part through and through. So I'll also, that's one of my other things to do is see if I can talk to someone and just get someone who is started on a lathe to just run the part for me, because that would make life easier and that would just solve a lot of problems. So
or you can, like, it seems like, wait, are you seeing you certified for mill?
yeah, that was the other thing was do just like a 3+1 basically on the trunnion.
What do you mean +1?
Well, like to basically turn it sideways and rotate it, because it's going to be too long to go around like this. So you turn it like this and just rotate it as you're milling,
yeah,
you know, with like a ball end mill or something.
One thing we could look into is like doing 2 halves and then like joining them.
Okay.
Instead,
yeah.
Because that way you can do it as a 3-axis on each half.
Okay. Yeah, I'll definitely look into that too. I think just I haven't totally looked into all the options in terms of like the actual machining side yet, but that is definitely something I'll consider, since the fewer axes, the easier my life gets. And then the couplers take time. But if we do this, that will solve that problem. So yeah, we just need to like keep in mind that weight reduction program is a pain in the ass to run.
You mentioned how the like 3D printing is no go because of the problem.
Yeah.
So what we have done is also before the studio way for this is we actually like we made the negative for them. Then we made more open.
Yeah.
Out of fiberglass. And then we made actual thing inside that.
Yeah.
That's
what we were thinking. We did talk about that briefly. I just forgot, I guess, to put that in the slides. But that was one thing we were considering doing, was making a fiberglass mold off a 3D print. And then
one more thing I want to ask about polling. Are you gonna have a way to measure afterwards to actually measure how?
Yeah, there's an optical comparator. Or there's also like a microview machine, Spectra or something in there that we can run. So yeah, I don't know that one. I have a feeling the O-ring group, that'll be like a bit lower priority. Like we'll do everything, and then like if we've got time, we'll try to grind the tool. But if not, I think we can just approximate based off of the profile they gave us. It doesn't need to be a very perfect profile.
Yeah.
So
all the like
yeah.
The angle doesn't really matter, it's the depth.
Okay, yeah, we can definitely check the depth. There's an optical comparator, so that won't be a problem. Checking the depth.
Depth and surface finish at the bottom, where it's actually going to be sealing.
Okay.
Or
you're probably don't actually care all much. Like you probably have pretty substantial because you release gas into the cavity very fast.
Yeah.
So if some of it is escaping, that's okay.
Okay.
You have such a short time frame.
Gotcha.
So yeah, like what I would be worried about more than anything. So it's a radial seal, right? So you have an O-ring on the shaft.
You slide the body to
if you make it the O-ring group too deep, obviously will not get compression.
Yeah.
And then something. if you make it too shallow, the O-ring is gonna extrude when you try to.
Yeah.
So that's why the depth is actually what matters here.
Okay, yeah, I'll definitely
Finish
check that.
process matters, but like, yeah, depth for sure.
Okay, and I also think like worst case, right? Like there's a decent amount of space here. So if for some reason the depth does get screwed up, we can just regroove it lower or higher. Like you would just like this, just you just make sure the O-ring. I mean, it just adds a little bit of extra like space,
And if you just have that, like you make it per spec with the requirements, and it's too challenging to push the thing into the thing because there's too much O-ring interference, and you have hard time lining up your thing straight. You could consider making your O-ring deeper, but put O-rings in there.
Okay, sounds good. Yeah, we definitely plan on buying a few extra O-rings just because that is like basically one of the most critical parts in terms of like the rocket working, and to like have not enough O-rings or have a failure where we could just buy a few extra O-rings.
I just display them, got like diameter circle O-ring.
Yeah.
It's usually as good to buy O-ring stock. It's just a very long piece of round thing, and you glue the two ends. It works surprisingly.
Okay.
In fact, it works so well. I have seen that done on Dragon for them.
Okay, I'll look into that too.
It's like you do get a little bit of imperfection in the contact point, but it's actually not like.
Okay, yeah, I'll look into that too as a backup. I mean, these O-rings aren't crazy expensive in terms of like all the other components, so I'm not too worried about cost being a factor. But yeah, so and then the last problem right now is the water jet is non-operational. So I don't really know the timeline is on that. Eric is out there like trying to fix it every single day. I think it maybe got fixed and then somebody broke it again immediately after, running like one part. So yeah, I'm not really sure what that timeline is, but racing needs it, senior project needs it, clubs need it. So I think it's like a pretty high priority, and I don't foresee a future in which it is not fixed by the time we would need it. Worst comes to worst, we can probably there's a TL or a tool room mill. We could probably mill the profile, like just make a plate and mill like a 2D contour if we really need the fins to be that shape and we can't cut them by hand. That would be an interesting experience, but
why would you not be able to cut it by hand?
I don't know. I mean, like if you're trying to just get the compound curve on the fins, or I don't know if the fins square. Okay. Okay. Then if they're just not like square, then we're chilling. Yeah, we could just do it on a tile saw. So yeah, then there shouldn't be much of an issue with that. But yeah, hopefully the water jet gets fixed. That's pretty much all I've got for manufacturing right now. Any questions about any of that or any specifics?
You said you might be looking at threading something.
Yeah, so that would just be basically one of the ideas we toyed with was basically threading here and then threading the bulkheads in like this, but that would just require thread milling. And that's, I mean, those I need to buy them for senior project and they're like $200 a thread mill. So probably want to avoid doing that. So I think we would just have these solid and have a threaded hole that goes in this way and have a clearance hole here and bolt it all together like that.
Nice inserts that will process the large amounts because we were threaded things for kitchen 7 heavy. Like it was like our tank for knives.
Yeah.
The tank was 2 and caps that we put it in. Those have to be laid down like outside.
Yeah.
And for this diameter, you're looking at the internal thread of like so 7.25 or something each.
Yeah, yeah, it's gonna be pretty.
I mean, that I think that was sized to be like well that because we were looking at like 9-inch diameter thing, so it would work.
Yeah, no, I think it would work, but I think that it would be it would just make stuff a lot more complicated because it adds a CNC what's the word I'm looking for? It adds like a CNC part to a part that's pretty much otherwise like manual.
You can manual in machine that's
okay.
It's so impressive.
Yeah.
You try a couple times and then figure it out.
Well, if this is built, I don't know. The cost of trying a couple of times will be pretty substantial.
Like the reds are. I mean, I made those tanks on the lathe.
Oh yeah, you totally. Okay, yeah, I guess you totally could do it on the lathe. Yeah.
And like, and by the way, if you run into an issue with the diameter or like size of your tube, which is like an actual thing that you run into, the ag shop has a gigantic.
Oh, I've seen it, I know.
Very exciting to work on.
Yeah.
Virgil, the guy that runs the shop, I hope he still does. He's the greatest dude ever. You should probably not be wearing the jeans you're wearing right now.
Yeah, I know. I shouldn't be wearing
Very
that.
good boots if you have a friend. who
Yeah.
wears those.
I have boots, so yeah.
Yeah, perfect. Wear both of those in a flannel shirt.
Okay.
He's gonna love it.
Yeah, that was my like very, very like, okay. Yeah, that was like, if everything goes wrong, I know the braid department has like a huge 12-foot lathe.
It's actually like a pretty cool thing, and I would honestly like recommend at some point to try it out.
Okay.
On this project, but in general, and like you guys should like consider that if you make a big at the end of the thing.
Yeah, yeah, the 7.5 was pretty much at the end, like I just flipped a 3-jaw, but yeah, it's gonna be pretty maxed out, so it'll be
Those little things.
yeah. So yeah, that's all I got right now.
Okay, I'm the other Cameron. And I'm here to talk about avionics. So we just kind of have a slide here talking about the PDR takeaways and some of our goals for CDR, kind of acting as like what we're going to talk about. We wanted to have a little bit more redundancy in critical systems, have a more solid manufacturing plan and testing plan than we did for PDR. I'm just going to kind of go into our design. These are kind of like the key design stuff that we developed. Some mounting plates for all of our PCBs and stuff is modular on these rods, can slide up and down depending on what we designed. We know where they're going now, but it was kind of nice to have this modular. We can use it again, that kind of thing. We have this is what they talked about for going into the coupler, and then screws into the sides is our base plate for the entire avionics stack. And we'll have threaded rods coming up.
What is that coupler going to be made out of?
Aluminum.
Aluminum, okay.
So is that a water jet? Or that was the lathe cover? Okay.
Yeah, so this that's probably what have
Yeah.
to do. Yeah.
I thought we made the change for that to be made out of plywood. Agreements.
We considered it, but we considered it, and then we talked to structures and they said,
okay,
that's probably a no.
Because I thought that part wasn't taking any load.
I thought it was something about the threading.
There's 4 screws in there, so that's
Yeah.
I think the threading into the couplers.
Yeah.
Comes into play if we want to use that thread into it. Definitely don't want to be threading into the grain of plywood.
It's also very thin. If this were out of plywood and we're stringing to like a centimeter or less, might not be as fun of a time.
Yeah, like usually what you can do is you just like hog out a hole and then put it in there and pocket it in. And so then you're actually threading into it, not the.
Oh, sure.
Like if you guys got to carry any wood anywhere else, something to consider doing it out of wood as well.
Sure. Oh, and then key design rationales that we just talked about the base plate, mounting plates, and then redundant altimeters will go into. That was kind of part of the previous slide with the redundancy that we added in an extra of the self-contained altimeters. So this is kind of our full stack model as of now. You can see kind of those modular plates with PCBs. We have our flight board. This is kind of the placeholder we'll have once we have it printed. It'll look a little different. We have power board in there, and then there's holes here for where the camera and the arming rod will go in with the battery. Zach, what's up?
We were also planning on printing the payloads mount, and I don't see like a line.
There should be one there. You're right.
You know what I'm talking about right here? Okay, so these two are going to be separate?
They should be, yeah.
Okay.
I know what you're talking about. I've seen both parts. It just doesn't look like got a line there in the model. I don't know how that happened, but yeah. Any questions on this design?
You stop that top plate from just like, you have spacers on there.
Yeah, so there's spacers here, and we can do the same thing on here. Mostly we're thinking because it's threaded rods all the way down, we have nuts and just epoxy them on either side here. The whole thing is threaded, the whole rod.
And what are those two antenna for? We only have one radio system.
The RFD 900 Plus is the 2 antennas.
That's 2?
P900 Plus has 2 antennas. Yeah.
Interesting.
You can run it with one, but it has 2 slots, and I mean, if we have the ability to buy 2, they're pretty cheap.
Totally.
Might as well. It wouldn't be mounted exactly like this because the 900 Plus, unless we had cords running. This was just kind of the way that the best. We had extra space on the rod, and so we'll probably be able to have them a little bit more.
Okay, and then
vertical.
Just about wiring.
Mhm.
We're going to be, I guess it'll all go through one of those various holes.
Yeah, so these are all like wiring ports here that we can run that through.
Okay.
Because my question then is there, so obviously you're saying it's a stand-in for the actual boards that you're gonna be printing.
They're not gonna be that large.
Okay,
Yeah,
that's what I was gonna ask. There's gonna be more clearance to run wires through the holes in the mounting plates.
Mhm.
Okay.
Are you planning on having the?
They're pretty. They're pretty.
This is 7.5.
Those
inches.
There'll be room.
Okay, I was gonna say a 7.5 inch whiteboard.
Yeah.
Yeah, so that's kind of all we have for this slide. This is a little bit more in depth on the flight computer. Most of the like pinouts and stuff that we have here for GPS system, the eMatch and the eMatch stuff here is not going to be used for the flight computer. It's just there for future use if we need it. The eMatches are all going to be controlled by the self-contained altimeters for this mission. And we're basically just piggybacking a Teensy for the microcontroller, Teensy 4.1. We kind of went into a lot more of the part selection details in PDR, but if anybody has questions, I'd be willing to go over it. Cool. And then this is just kind of review from PDR. We talked about this as well. Control cycle, having kind of 4 main stages of data collection with all the sensors, and then status updates, check to see what the data values are against our thresholds that were kind of gone over in the ConOp slide. And then systems control, if there's things that need to be sent, that would be from those. Really the only systems controls we have in this mission would be from the self-contained altimeters, but nothing from the flight board for this mission. And then transmission and log, we have to transmit the live telemetry and then log it to the flash storage. And then once we're in a stable spot, we can put it in the SD card.
What control is actually being performed? Is it just like popping the chutes?
Yeah, popping the chutes and the pressure vessel. And that's all done by the self-contained altimeters. Nothing on the flight board is actually controlling that. The flight board's just for telemetry for this mission.
You guys don't have any access to the logic that controls that, right?
That controls the
command shoots out.
Well, so we only really have access to the thresholds on the self-contained altimeters, the stratologgers. We have the ability to hook this in as a backup if needed. We just figured since we have 2 already redundant systems, adding a 3rd may not be necessary.
Yeah. Going down rabbit hole in my mind.
Sure.
I remember there was some sort of a dust or sand issue.
Yeah, that's in here. We're getting conformal coating to spray down all the electronics to seal them from weathering, water, dust, any sort of stuff like that. So we'll just put on gas masks and spray all the electronics down when we need to do that. So yeah, I guess this is our cost and weight budget analysis here. Nothing too crazy to say about this other than we're like the maximum here is for avionics and payloads, and all the weight calculations here I did were for just the avionics section. So this stuff down here, the CubeSat, I didn't include, and the base plate was included with manufacturing for the total weight or structures.
You say that the base plates are made of?
These ones are likely to be 3D printed. And then this one is aluminum just because it has to hold a lot more. But sounds like plywood might be an option if we do nuts. Instead of
just like do some sort of blast or like something.
Sure.
And just I don't know, laser rather than 3D printing on.
That's probably more structurally viable.
And then are you guys like getting PCBs printed like from some external?
Yeah.
Doing all of this. You guys are doing all of this soldering components?
Yeah, we
Yeah.
just went to the workstation.
Okay, are you guys gonna be doing any like testing before you go and?
Yeah. Yeah.
Like,
So we're going to be doing testing just as we go through and soldering the components. If we have any electrical engineers in here who have any advice, we would love to hear it. We are also doing spice simulations. So like we have, at least for my systems, I've done spices or LP spice simulation for everything just before I put my own greedy little hands on the budget and said bye. So that's gonna be in our testing process. So we know that it works, and then we're just gonna go through and make sure that we've soldered on all the components correctly. Do you have anything to add? No?
So I don't know if there are shake tables on campus, but like being able to, it's like for vibe testing.
Oh,
so it's essentially,
Oh.
it's like a speaker essentially.
That'd be super nice.
It's
Yeah.
the same, like hardware for a speaker and then like hook it up to a table.
Yeah.
And that way you can take it, you can mount it in different directions, so that way you can.
Are you talking about the board specifically or what?
Yeah, so like, as you go to industry, you'll start to see like a lot of shake tests on A by stuff.
That'd be super nice.
Like, you have a lot of small tiny elements that if you don't have a perfect solder joint, will lie loose and like lose whatever A by
Yeah.
you have in that.
And the other main concern was we have an SD card. And the way we're trying to deal with that is just not even write to it until we're stationary.
Yeah, because all your contacts can be like
Yeah.
bouncing around.
Yeah. But yeah, that'd be super nice. We should look into if there's one on campus.
There is,
Okay.
there is one, I was, before E12 got canceled,
Uh-huh.
I was very briefly in the ground support equipment team.
Okay.
Which was, so I was gonna be working with vibration tables, so I know where it is, and I have a
Sweet.
little bit of info about it.
Yeah.
But not a lot, because I was there for about 2 or 3 weeks before it.
Sure.
So-
We'll definitely have to talk to some people about getting access.
Did they actually make? Actually producing, right? Is that? It's like a very non-trivial challenge to make one. It's not a trivial challenge to a degree that we don't have one surface, we only have one multiple platform. Because we're like, that's too much fucking trouble.
Yeah, we were looking into like the manuals and stuff, because basically at that point, I guess nobody really knew how to run it. That was.
The objective of the test is to really shake your thing.
Yeah.
And if, you might be able to figure it out, but if you don't, you may be able to shake it in some other ways. Yes, take it for a rough ride.
Yeah, that was part of the testing as well. When we wanted to test like accelerometer accuracy and stuff, we were thinking we'd just put it in the back of a car and just, like that could work as well for a little bit of a shake test.
For all avionics that goes on any sort of flying vehicle.
Yeah.
Like after it's built and some simple checkouts and burn it, they always run at least minimum manufacturing level, which is like 4G is pretty benign.
Yeah.
But it's relevant to screen for like you can properly solve everything.
But that
Sure.
depends on like the orient, as you were saying, with doing that depends on the orientation.
Yes, it doesn't check.
Okay.
You do it just check. But like I said, for what you're trying to do, you might go shake filter.
Yeah.
Don't shock it. Like
What's
don't like drop it and think that if you drop it and it survives. Because shock induces micro damage that might not manifest itself 10 minutes later when you check it out, but will manifest itself on the final.
Let's say I'm a dumbass, because I kind of am, and I actually knock my shit off the table, and I'm like, dead, it's shot now. Is there any way that you guys would suggest going about testing that to be like, okay, my system is probably still okay to the launch?
There is nothing else.
Okay.
Just don't knock it off the table.
No.
I mean, testing helps like highlight HCF, or like I say, like high cycle fatigue that would like pop up because of any micro damage. But yeah, like and actually James Webb had this problem. Like they had some big vibe event right before they were gonna launch.
If you do something like that and you are looking for some, you should have another article to reach like build the second unit.
Oh yeah, what
and then drop that one multiple times, like, and that, a unit that you're not planning to fly. Then there might be defections of some sort, like you burn something, well, maybe the first ever, or like this doesn't work, or how it works. So you throw that one out, and then verify it works. That should give you confidence that whatever you just did to your flight point is probably okay. Interesting. Okay. That's called qualification.
And then like one thing that is done often in industry is like hypothesis testing, where you do like potential, where you apply the actual vehicle LRC. So that way, like even during your testing, you're not guaranteeing that you'll see max potential. And so like there might be something in there that fails as you get to higher potential. And so like going through and making sure that you hypothesize all joints that are actually going to see like varying voltage. Okay. And then also you also mentioned it earlier of like burn-in tests where you like leave it running for an amount of time because it's like a bathtub curve, it's called, where it's like you have a high infancy mortality rate, where it's like if you plot if you plot like time versus percent of failure, how do you like this percent of failure? You'll have a lot of them that are going to fall out early because you have like something wrong with your manufacturing. But then like these ones are going to be able to last longer amount of time just because like everything to the right has decent manufacturing, and then as you just go on further and further, you're going to have these guys just due to old age. But like doing burn-in tests will allow you to like remove this part of the topic. So look up.
Yeah, I was gonna say, is there any material?
I'm sure Google has material.
And just burn.
Yeah, burn-in tests for avionics stuff.
All right. So moving on to like what we're planning on testing, some of the key targets for the flight board is we just kind of wanted to make sure the accuracy of the systems is good to get accurate data. I mean, that's kind of the ultimate goal for the flight board. And the testing plan, we're going to like build some rigs for the self-contained components. We want to make sure that they have accurate apogee detection, just because we're not the ones who are actually building that software, and it'd be nice to make sure that it works. And then we'd just like log the data on a TT in the rig, and then look through it and make sure it's correct. And then we want to also do for the like flight board with the onboard stuff, because we have a altimeter and accelerometer on our flight board. I want to make sure that that is accurate so we can get good readings. That's not as mission critical as the self-contained ones, but it'd be nice to test. And then we also want to make sure that the logging works for the SD, because that's one of the requirements for FAR that we're trying to hit. And make sure that we can flash all of the data for as long as the flight would continue, and then be able to fit it all on the SD. The SD is not as much of a problem as having enough flash storage on the TNC. We should have enough if it's the length of flight that we're expecting. And then GPS as a recovery strategy is also something that we wanted to test. That currently the idea is that we'll have the GPS still transmit after the rocket is grounded. If we don't see it, we just go up on a hill, get GPS data to the ground computer, and then follow it.
Does it require going up on a hill to get the signal?
No, we should have signal like a last known location if it doesn't have line of sight to us while it's on the ground though, and we can't find it from the last known GPS
There's just
pin.
not really a hill
Okay.
near far
Sure.
to count on that.
Yeah.
There is like a
Oh, there is a test stand, yeah.
One other thing is, are you guys doing testing for like how far away?
Yeah, that's in the next
Yeah,
telemetry transmission tests we also have to do. So we want to make sure long ranges, varied angles, varied like materials that is transmitting through. What we'll find on the rocket is fiberglass and carbon fiber. We have little hope to get through the carbon fiber, so we're just hoping that the angle that we have, testing the angles around the like through the other materials is what we're trying to transmit through, and make sure that those angles work, that while the rocket's in flight, we'll still be able to get line of sight through the carbon or not carbon fiber materials.
I mean, this might be overkill. Have you guys done a link budget for this?
A what budget?
A link budget. any era seniors getting traumatized by this. I'm glad. I don't know about electronics to know if you guys really need to do a link budget for this, but it's something to consider.
Okay,
Is it
Yeah.
really, is it really important? Like what you're.
I mean, it tells you whether or not you communicate.
Yeah.
So, point, just rest the rest of us to know what you're talking about.
Okay, perfect. No, I swear to God, link budget when you're doing.
Space.
Yeah, it's a learning experience. It essentially tells you like how well your electronic system will be able to like figure out what is normal and what's actual signal running around.
Yeah, like based off of like transit power and size.
Yeah.
You didn't take comes from power, you find out.
Wait, are you arrows or not?
I'm arrow, but I thought myself.
Okay.
Oh, weirdo.
Yeah, so basically, like for the range test, we're just gonna have someone stand up there with the flight computer on like the P or something, and then just walk really far away with line of sight, and then have it at different angles, try to transmit through carbon fiber, or sorry, the other one, fiberglass. That kind of thing. Manufacturing schedule is the other thing that we need to talk about. So I just kind of have a preliminary order of events, what's dependent on what, and before we can start putting stuff together, because we've got a lot of moving parts. We got to make sure that the outsourced components get here. We're going to order those and the PCBs first, then start printing and cutting in-house components like the mounting plates and the base plate, and then assembling the rods and stuff that we're ordering, putting all the PCBs onto the mounting plates, making sure all that works, and then the wiring is the last step once we have everything in place that's larger. That's all I have. Any other final remarks, concerns?
Just real quick, could you go back to the CAD model? Or, oh wait, no, that was. Okay. Just as a heads up, the altimeters and the peregrine and the assembly currently like go through each other.
Okay.
So they might need to be moved.
So yeah, I mean, we have extra space here that we can maneuver things. There's a lot of extra space in here too with the boards.
I think
we can squat down.
we just talk to each other and make sure that they're not projecting onto each other.
Yeah.
Because there's a ton of
you're
space.
saying
The
you just
couplers,
touch these?
yeah, couplers are.
Oh, okay.
So I
Yeah,
think
then
we
we
just
just
talk to each other
turn
and the
it,
couplers can be moved as well.
Yeah, so I guess that raises like a bigger question of who owns your guys' CAD structure for the assembly model?
It's,
Like, they're
on a cloud service.
Yeah, but is there like one singular person who will get the finger pointed at them if something interferes?
Gosh.
Like, okay, singular people point at each other. Like each lead or whoever is handling manufacturing for each team should like own their own assembly, but like there needs to be like one or two people making sure that things aren't just like running into each other and it's owning overall assembly.
Yeah, that's kind of the plan of what we're using Onshape. The plan is to have like sub-assemblies for system level kind of assemblies and then an overall like rocket assembly. And so, yeah, it still needs to kind of be set up completely, but the goal is to have it that way.
Okay, yeah, there just needs to be somebody who feels responsible for like incorporating all of those together, because like the problems will almost always pop up at interfaces between teams. So if avionics thinks that they're gonna have 4 things of all thread running through them, and structures is like, yeah, we're gonna have 5 things of all thread to support AVI, like there's gonna be a problem. So as long as somebody is having that overarching like view of it. It's good.
Sweet.
I guess another point in that, having this design review is great. You guys should have CAD spins, like on a regular basis. Like you just straight up sit in the same room for half an hour, here's that room, and just pull the CAD out. Don't need to prepare any slides for it, like analysis may or may not have it. Sometimes it will take 15 minutes, sometimes it will take 3 hours. But like you should just have them regularly. You would be amazed at shit that happens sometimes just because 2 people that are working right next to each other don't have the same assembly load. just to from this. It's not really for your question, but general for the group, the 10,000 feet requirement. Are they gonna ask you to provide the data from altimeters that you place in the vehicle? Or are they?
Yes. So they have approved altimeters that we're supposed to source and put in, and that's what those two redundant.
Yeah, so I got that you have two, there's like recommending for the deployment process and whatnot, but like the actual data that they'll use to give you score, is that gonna come from them?
Coming from those
They're gonna give you a thing that will be like, attach this to your vehicle, and then we will take it from you and we will read it from you. And don't fuck with it.
The board beats it out.
Yeah, so we use the board beeping to read the altimeter.
So it's your hardware, they don't give you any.
Yeah, as long as it's an approved device, we can source it and place and insert it into our vehicle.
You also go back to the spec. I didn't see any holes for mounting holes for the RFD. And I was wondering how we were going to mount that, as well as how we're going to make sure that when the rocket launches, everything doesn't just smash. Like,
so the RFD would likely be on this plate. I think we were planning on having it at one point. It was underneath, and it might be in this still underneath. But we talked recently about not putting it underneath, so we still have to move it to the top. It would probably just go right in between these two if we moved it to the top. Because I know you were concerned about large loads pulling it off of the mount. So yeah, we'll move that up to the top and mount it there.
I just didn't know if it was modeled and then if it was how we were connecting it.
Yeah, sure.
But if that's something go over, that's great.
I think it also has the ability to piggyback onto a board if we wanted to put it on the flight board.
Really?
It looks like it has pins for that.
Yeah, I just made eye opens for it, but I can make an actual shield.
Yeah, I mean, we could. That might be too complex. I think right now we just mount it as we thought, just on the other side of that mount.
Then when you go to the top of the chutes, do you have to worry about CO2 getting into this cavity at all or no?
No.
Okay. And then thermals should probably be fine, but like you might want to test that up to.
Sure.
Yeah, we have
however many degrees we expect that to be.
Yeah, we also have heat sinks on all of our energy intensive devices. So on our RFD 9000, we got heat sinks on both, as well as on our video transmission.
Yeah,
so it's like anything
it's like a heat sink. It's like a heat sink to fins, right? Like you'll have like your component with a heat sink and then you have fins to try and keep away from there. If your ambient air temperature is 110 degrees, you're not.
Those heat sinks are gonna matter.
They still matter some, but like if you're in the desert, like it's harder to get heat away. We actually had.
What did you guys do?
We had. Remember that time that Hal just died? We had like our main thing that we used to like.
It's a very different problem. You're gonna be experiencing thermal alarm for a very brief period of time. Is this? I don't care about as much about your heat sink is the thing. It's thermal mass. If you start to come to that, your surroundings look under that. You're expected your surroundings for 5 seconds. By the end of this, if you're massive in that, you're going to be still under that, plus 2 degrees. With the hull, the problem was the ground support computer that was sitting in the center of that. It was just overheating, just like that's it needed bigger fans. You don't have to scope. Like you definitely need to check these things and you size them seems to be appropriate, but you don't need to seriously consider how hot it's gonna get up there because it's not.
No, I'm not saying like in flight. I'm saying like if you're sitting there for the entire day, you're going to equilibrate with like air temps. As you traditional, and then you only get working. Regardless, you should be tested in the environment that you're going to be like actually flying at. Like if you're testing while it's 72 out, and when you go to that, it's gonna be different. Surprisingly.
Sounds good. Wait, okay.
Okay, so I had some really exciting slides prepared. They have since been tarnished, so I've added what I could in the past 5 minutes. My team, I have some really great people. I have Devin Bolt, he's an electrical engineer. He's been helping me with my op-amp circuitry. I have Connor Scott, he's an amazing mechanical engineer helping me with simulations, just like you've been doing for wherever Will went. And then DJ and Ben Tucker will be helping me with cybernetics. I can go on to the next slide. It's a little bit of an overview on our stack up. Huh? Oh no, I'm Trace. I mean, but who cares about me? Like, people matter. Anyway, so this is gonna be our flight stack up. We'll have our little camera right here, which is what you were asking about. There are still going to be some changes to this device. We're going to be mounting a lot of radios in here. So we'll be mounting our camera radio, and I believe that's all. We will also be routing our power from this section. We'll have 3 18650 batteries routed in series. Now, the most important part for you guys, avionics, and then everyone, is how we're going to actually be routing out power. When we are going to be on the pad, we're not going to be we don't want to be on until we pull out our arming rod. In order to do that, we're providing a virtual ground for all of the devices running off of our battery system. And we're also going to be just turning off and on the enable pin via our arming rod when it's pulled out, which will turn on all of our 3V and or 3V3 and 5V power systems. We also have our pinouts and a little nice LED to show everyone, okay, our board is on and it's running. Any questions?
This is kind of a dumb question. What's the difference between a virtual ground and an actual ground?
Hold on. So what the virtual ground is going to be able to do is it's going to act as a switch for all of our devices running off of our powers, off of the batteries. Like, how do I describe this? It's like a connection to ground. You could picture it as me taking, in all intents and purposes, it's like a switch. If I had 2 little plates, I'd switch it on and it's like, okay, now it's connected to the ground and all these devices are firing and they're on. And then when we put that enable or the arming rod back in, that opens the switch back up and our devices on the battery system will no longer be on. We also have a small little capacitor here. I would love to talk to someone who knows more about this than I do about this capacitor. We were a little bit worried about rattling around and that turning off and on the arming pin. So we added a capacitor which would be able to supply enough current to the enable pin of our of our MOSFET, as well as our 5V buck boost converter, in order to keep those systems running if the enable pin was to like disconnect for a couple of seconds. So if you guys have any information on like how to choose that capacitor, please let me know.
You guys looked at, so you have an arming pin, it's like a physical pin that you insert.
Arming rod, yeah.
Yeah. Have you guys looked at like magnetic switches and all that?
Magnetic switches kind of run into the same issue. I've heard that you just want a physical thing to rip out and it would feel nice, you know. All right, it's on. We know that it's on, you know. Yeah, I gotta put it on my backpack like everyone here. That'd be cool. Yes.
Just here. Sure. So we have one power source for both payloads and avionics, right?
Yes. Okay, this is the operational amplification circuit that we're going to be using to detect the action potentials. We'll take a -5 millivolt input through each one of these. These are all copies of each other, so we could just look at one of these models. It'll take a -5 millivolt input from an action potential and then run it through this inverting LM7 or an LM741 op amp in an inverting configuration to flip the voltage from -5 millivolts to positive 3.3 volts. And then we also just have active bandpass filtering with the second LM741. All fun stuff. And this was designed by me and Devin Bolt. He's a cool guy. And then testing and assembly, as I was talking about earlier, we ran LT Spice simulations to make sure that all of our shit was going to work before we started to buy stuff. And that's kind of all. I told you I'd get you guys out of here pretty quickly. Anyway, thank you.
Also gonna recommend vibe testing.
Vibe testing? Yeah.
Avionics, or like just make sure that you guys are aligned in your testing approaches.
Just write the program. Build it another.
Trace, have you written up a power budget for this to make sure, like, how much
Yes.
runtime are you
You
expecting?
have the power budget here.
Yes.
Have you accounted for, can you run us through how long can we stay on the pad while armed before we have to screw up?
That's a fair question.
That's a fair question. I'm gonna be honest with you guys, I haven't run through that. I was just making sure that we have enough power for like 2 or 3 hours.
Okay.
But I still would like to give a better number for you guys.
Okay, so like at minimum 2 hours, or yeah, so we can stay for at least 2 hours on the pad.
Yeah, let me get back to you guys on that. But thank you for bringing that up.
The person who's responsible for pulling the pin out, also have a stopwatch. As they pull the pin out, they give the clock.
Interesting, okay.
And then they'll just say that for whatever reason, we just run 3 hours. They're like,
Totally, that's what's smart, yeah.
One other thing that you guys can do if you're like really concerned about having enough light and you don't want to add massive rocket, you should do like another breakaway connection that like.
Yeah.
Yeah, you have a pin that goes in and then as you want it disconnects.
Yeah,
So that way you
do that.
allow access to the batteries.
I like, in all honesty, I'm still pretty new to electrical design, so. If you guys have, if you guys have like a way to do that.
Concern with the breakaway is that we wanted to like have on-pad calibration of telemetry transmission, make sure that we receive it. Would that still work with the breakaway?
No, you're saying you pull the pin out and then you're starting with.
Yeah.
Yeah, you have your on pads, like you have your GSE power, that's what, so you can like turn it off or fucking plug it.
Sure.
Like
Yeah.
do your one check and then plug back in, and then send theirs.
Yes.
How do you design it? You just install the pin back in?
Yeah.
Where is the pin port?
That is one of the things I forgot to say. It's going to be located in the payload spec. That was another thing I was doing.
How high is that and how accessible is that when you're on walk?
I don't know.
Won't be on the ground, they'll have like a flame diverter and then they'll be up higher, so like if you can access it on the ground here, so that's not guaranteed you can access it.
That's good.
Without like a ladder or something.
Totally really long, royal case. Okay.
You might be it's cool.
Oh, yeah.
Ours, like this.
No. Interesting. How high was this? Because
we had like a magnet on a stick.
Oh my god. No way. It was way. Okay. Anyway.
That was horrible because like very little way to verify actually this.
Yeah, like, and I was actually just thinking about that. You guys should have some sort of visual, like, light or some indication that everything is armed.
Okay.
Goes
like a buzzer.
yeah, something.
We had a buzzer last year.
Yeah, I think we wanted to add a buzzer to
avionics.
Avionics, whiteboard if possible.
Yeah.
Buzzer is simpler because then you don't have to allow flashing thing.
Yeah, but every time Marius wants to arm the system, he'd be like, all right, everybody shut up. And then he'd be like, is that a sound or not?
It was like, I didn't go to the launch last year. I'm sorry to cut you off. I didn't go to the launch last year, but when you guys pulled the pin out last year, could you hear?
Yes.
Right,
Yeah.
okay.
It was loud.
We accidentally pulled the pin in front of the Lockheed person.
It's-
Yeah, it was very scary.
Can we get LED strips and have an RGB gamer payload?
I was thinking about that, okay? I have a new design. Hold on. Okay, who's next?
Okay. All right, so I got just a couple final words. Total approximate budget, we're around 4,500 plus or minus 500, given whether we have some materials, whether we need to get some extra materials, kind of that. So that's the range of things right now. I don't think that considers, I guess, extra manufacturing costs. So that'll be something else we'll have to consider. We'll have I guess we'll add a separate bill of materials just for like manufacturing equipment and stuff like that. But yeah, so I guess the next steps from, question.
I would recommend not having a lower round. You have plus minus 500. I don't think you have minus 500. If it's cheaper than 4,000, it's a win.
I guess that's fair. That's the positive side, that maybe it is cheaper. Who knows? But yeah, so I guess the takeaways from this presentation are the feedback we get. We'll just integrate that with our overall design and systems documentation. Before we start manufacturing, I want more detailed like drawing and part files, just so we know exactly what they're going to look like. And that'll just take, you know, some of the feedback of integrating everything before we can actually do that. Yeah.
Oh, sorry.
Okay. With that, finalizing the bill of materials, specifically kind of the actual components of the rocket, and then probably secondly, and we'll probably continue into manufacturing, is like manufacturing costs. But making sure we know what material we need to buy for the rocket, which stuff we already have, what's going to be donated, all of that kind of stuff. And then just creating some detail, or just having a more detailed testing and manufacturing schedule, given how much manufacturing is going to happen in the rest of the year. We're going to want to kind of know how that's going to work and just be really detailed about that, but that'll be to come. And then, yeah, begin manufacturing. That's the goal. So yeah, thank you all for coming. Yeah.
Are we getting pizza?
Yeah, it should be.
Menu.
Here
We should just scroll.
20 minutes.
No, don't show them the requirements. I don't want to show the requirements. I don't want requirements. There's so much that could be changed. Sorry, we did it. It's not me. I'm not in control.
You get something better.
Okay. Hello,